Good to see you again. Thank you.
कौन
प्रोजेक्ट बना रहे सर? हाँ हाँ बना रहे गड्डी चल चल के लेवल लेवल चेक करना था चल के अभी
सेवन एवन एच ठीक है ठीक है ठीक है
हेलो 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 ਕਿਹੜੀ ਲੱਗਣੀ ਹੈ? ਇਹੀ ਵਾਲੀ ਲੱਗਣੀ ਹੈ ਜਿਹੜੀ ਚਿੱਟੀ ਲੱਗੀ ਹੈ ਇਹੀ ਲੱਗਣੀ ਹੈ? ਤਿੰਨ ਪਿਨ ਵਾਲੀ ਤਿੰਨ ਪਿਨ ਵਾਲੀ ਨਹੀਂ। ਜੋਤੀ ਸਰ ਨੂੰ ਪੁੱਛੋ ਜਿਹੜੇ ਮੋਬਾਈਲ ਤੇ ਲੱਗੇ ਇਹਨਾਂ ਨੂੰ ਪੁੱਛੋ। चार्जर है लैपटॉप का चाहिए।
ਆ ਦੇਖੋ ਨਾ ਇਹਦੀ ਆਵਾਜ਼ ਆਏਗੀ ਉਹ ਮਾਈਕ ਸਰ ਇਹ ਵੀ
हाँ जी
ਇਹ ਮਾਈਕ
नॉट रिक्वायर्ड माइक इज नॉट
ਨਹੀਂ ਸਰ
रिक्वायर्ड
ਇਹ ਲਾਈਵ ਵਾਲੀ ਜਿਹੜੀ ਆਡੀਓ ਹੈ ਨਾ ਇਹਦੇ
अच्छा
ਤੋਂ ਜਾ ਰਹੀ
फॉर
ਹੈ।
द बट नो
ਇਹਨੂੰ ਕਿੱਥੇ ਵੀ ਰੱਖ ਰਹੇ ਨੇ ਇਧਰ
if the laptop will play a video
ਜੀ ਸਰ
from where do I send the audio to your speaker please do that speaker पे आवाज आ जाए
I put yesterday, I put the microphone on the laptop speaker. That's a quick
Pardon
solution.
me?
Yesterday, I put the microphone that was attached to my clothing.
no but when the
Yeah.
HDMI is connected
Yeah,
it
it
will
should
not
be.
work when
Yesterday, on my laptop still it came. I expected it to come out of a speaker, but there was no.
oh,
So it came out of my laptop.
so this was a box that was available in the market so the challenge was just placed it there it goes into these 4 holes for location then just lock and then drill so there also 3D printing can help because this box it had ribs and all that so sometimes you would just drill a hole from inside and when you're going to tighten the nut you see oh, the rib is there so
Yeah.
it can't fit
So you need
so
to.
everything was done in the CAD model and then just made this template pasted one iteration got fixed then using a OHP marker we did the marking then drill
And then.
saves you lots and lots of time otherwise just drilling process being iterative in,
Yeah.
in
Well,
nature
once you're there with drill, that's the point where you
Yeah.
otherwise.
a printer, earlier times they used to be handwritten, right? Then variation is concerning the change in the level of demand. So today something is in demand, tomorrow something else is going to be in demand, so you have to change the block in the printer, maybe the tooling for the manufactured parts frequently. So depending on variation in the product variety. If let's say you have facility for making parts and you are catering to 100 different customers, maybe 100 different clients for whom you are making the products. If one client cuts down the today and another one increases the demand, then if you have a flexible manufacturing system, then you can tooling set, then you can watch a number of videos on YouTube or various OTT platforms concerning how Rolex had progressed in becoming a popular brand across the globe. And the challenges which they faced, those challenges were the World War I and World War II. They converted all their challenges into opportunities, and today they are brand to brand. So that's the example I'm used to quote. Okay. So visibility is how well you can connect. How would you like if, let's say, your toothbrush, you keep it at some place in the home, and somebody else might happen to pick up yours, and you'll have to throw it away. Right? Likewise for spoons in the mess. What if you have your names printed on them? Have you ever thought? Why have only Colgate printed on the toothbrush? Why not your name? Likewise for hairband or clips or whatever. All personal items, if they have your name engraved or printed on them, then anyone will be warned, okay, this doesn't belong to me, even if the items are looking identical otherwise. Right? So that way 3D printing can serve the purpose, because otherwise for just one hairband or one toothbrush you'll have to make fresh tooling which will cost you lakhs of rupees, and then making just one or two toothbrushes will not be viable. It will increase the cost of the product. That customized toothbrush through the conventional process may cost you something like 50,000 bucks. Otherwise it will cost you just 50 bucks. So that's how the variety and the demand, all that, right? It depends, it dictates the manufacturing process. So the conventional processes are basically meant for large production volumes with very limited variety. But 3D printing can cater to very large variety but with a relatively limited volume. So understand these V's, variety and volume, right? Can we proceed ahead? Yes. So I'll just give you a brief outline about the conventional product development processes. There are basically three kinds of approaches by which we can develop a process. One is formative. You have a mold, you pour some molten material, maybe a metal or a plastic into that, and it forms the product. This first one. Then you have subtractive ones. Subtractive, what we do is we start with a bulk material, then we cut out the unwanted portion just as we do sculpting. The sculptor does sculpting as you have here before you. Right? Remove the unwanted ones, and then you are left with the desired product. And this third one is additive. This is the new entrant to this group, where the material is deposited just as required. You see, the first two have substantial wastages. The third one has very limited wastages. You just use just as much as is required. Right? पहले में आपका मोल्ड वेस्ट हो रहा है, कुछ मटेरियल भी ऊपर से काटना पड़ा आपको. सेकंड वन में आप बहुत सारा कटिंग करके चिप्स की फॉर्म में रिमूव करते हो, बट थर्ड में देयर इज हार्डली एनीथिंग टू रिमूव. सो द पार्ट्स व्हिच यू होल्डिंग इन हैंड दे आर इन द जस्ट एज प्रिंटेड फॉर्म. हो सकता है आपको हल्की सी फिनिशिंग ब्लेड के साथ इन पे करनी पड़े, दैट्स इट. Even that can be taken care of by parameters. I don't know why this is not working. Anyhow. Okay, so this is one thing which I just wanted to show you how 3D printing can help, and it also signifies the designing approach using CAD software. So, ma'am, this is a weather station for precision agriculture application. So it has got sensors for temperature, humidity, and solar insolation, how much sunlight we're getting, and wind speed and all that. So this box is just to protect the components from atmosphere, and then expose them like humidity sensor has to be. Right? It is mounted at the bottom, you can see, and then we have soil moisture sensor, and then a microcontroller and SIM808 module for transmitting the data via mobile network, via the GSM network. So it does all this, it records the parameters and then transmits to the cloud server at some prefixed interval of say a few seconds, around 15 seconds. It relays the information. So the data is getting collected. Now making this was a challenge in various ways, because once it is deployed, it's like sending a mission to the moon. You don't have access, or the access is very expensive. So this box is actually currently deployed in DCM's farms in Uttar Pradesh, and I can access the data. It's been there for 2 years now, right? And this is the actual one with all the wiring, and here's the comparison of the actual with the model, right? So assembling one box was a huge task. First you have to design the electronic circuit, you have to do the programming, and then you have to do the mechanical assembly. And mechanical assembly requires like drilling holes into a prefabricated box that you get on some platform like Amazon. And it used to take around 6 hours to assemble one box. Then what we did was, we resorted to a 3D printing solution. I'll just show it to you. This will give you a glimpse of the CAD approach. So this is in the CAD software. We modeled the entire box in the CAD. Then we modeled a drilling template that can be fixed at the bottom. So using an OSP marker, permanent marker, we can just mark the position of these holes and then remove the plate and quickly drill. So what used to take around 6 hours now can be done in a matter of 15 minutes. So that is how 3D printing it comes in handy for making components with limited volumes. Right? Now if we are to change the positioning of the boards in between, all we have to do is we have to just modify this bottom plate and then print a fresh one. That will take a couple of hours. No fixed tooling is required. This is a free and open source software. This is FreeCAD. FreeCAD. It's all free and open source. It's basically crowdsourced. You can download and install onto your machine. This is FreeCAD. I have a slide that will show you concerning various CAD software as well. The objective is to have you enabled today by the time you leave. Okay. Then the conventional process. This is concerning an agricultural tractor. We have a full-blown life-size sketch on the wall. The way we do all various checks. Then a wooden mock-up. Then the surface is scanned using a 3D scanner. Then some quality checks are performed on the surface, and then detailed designing is done. Now once the detailed designing is done, then we go for assembly modeling. All the various components as they are going to be fitted on the actual part, right? They are designed, and once that designing is done, then we go for making the mold. This is a conventional process. So this is a CNC machine. The pellet goes in, and the robotic arm will fix the required tool as per the CNC program, and then the cutting is performed. The tools can be changed from the magazine as per the program, as per the requirement, and the cutting is performed. This is a conventional process. These machines usually they'll cost you something like 3 crore rupees. Then the per hour running cost is very high. The companies run them in 3 shifts, 24 hours a day. Right. Then you have AMC maintenance and all, then tooling cost, material cost, everything is very high. It's cutting a cavity right now, you can see in low alloy steel. Drilling operation. That is how most of your automobiles are manufactured. The tooling thereof. That is how it is made. Okay, done. Let's move to the next one. Now, after the tooling is done, we get the tooled up samples of the finished components. And here is an example of how the CAD model gets transformed into a physical component. But the cycle time is around 6 months from the model to the actual component. But once the 6 months the tooling is done, if you order them, okay, I need 3,000 of them per day, you can get them. Right? That's a kind of production volume, just like newspaper printing. Right? But now the problem is the tooling will have would have costed you crores of rupees. So if you want a subtle change in design, you have to spend the same amount of money again, and the old tooling becomes a crap. What an idea! Okay, so this is the final product. So whenever companies will launch a new product, they have to go through this entire phase because the production volumes are high. Now, on the contrary, additive manufacturing's journey is different. You again start with idea, you again have CAD model, but from CAD model we don't go with the programs for tooling and the machines. We straight away go for an STL file, which is a test related geometry file, and from there we make the NC part program, which goes to the 3D printer, and you get the printed output, just the way it is currently running a program which is loaded into a small memory card here. Now, some of the tools and techniques, you people being from chemistry, you must be knowing about the term enantiomers. What are enantiomers? Can somebody tell? If you heard the term, optically active materials. What do they do? They are mirror images. What do they do to the light? They rotate the plane of polarization. So we'll do a small experiment here. I have got 2 linear polarizers with me, which are difficult to get these days. Okay. What I'll do is place it before my mobile. Can you see the mobile screen through this? You can. If I turn one of these, does it dim? It is actually circularly polarized, so it's not dimming. Anyhow, let's use unpolarized light. iPhone is a pain. How can you switch on some lights? Thank you, thank you. Now it's good. Can you see my eye? You can see. Now let's turn it by 90 degrees. I'm gone. Turn it by another 90 degrees. Visible again. Right? So that is how a combination of a polarizer and analyzer, both are identical. It's just a placement. The first one is called as polarizer, the second one is called analyzer. So what polarizer does is it converts the unpolarized light into a plane polarized light. This is not a circular polarizer, this is a linear polarizer. The other one will stop the light. Now with this background, we can quickly have a recap of how the electromagnetic radiation works. So you have electric and magnetic fields. Then if you have conductors, closely spaced conductors, in the path of this beam, the electrical field along the conductors will get absorbed. Many books display this figure wrongly, right? So electrical field vector was going upward can pass through this because it will not interact with these horizontal conductors. The horizontal component of the field vector, it will get absorbed because the electrons will start dancing to that and it will absorb the horizontal component, and what you get is plane polarized light along the vertical plane. So it emerges. Now the next thing that we are going to have is we'll place a liquid crystal in between the polarizer and analyzer. You see the polarizer, this is along one plane, this is at 90 degrees, the analyzer one. So the light comes, right, and then this liquid crystal, it rotates the plane of polarization of the light by 90 degrees and then it can pass through the analyzer. But if you apply an electric field, turn the switch on, the liquid crystal molecules, they align as per the electric field and they can no longer rotate the plane of polarization and no light will pass through. So actually on your LCD displays, right, when the power is applied, the pixel becomes black. When there is no power, the pixel remains white. It's only the backlight that comes through. Right? This is how the LCD works. Now, Dr. Zain is using the same technology for polymerization 3D printers, resin-based 3D printers, because using this setup you can modulate the laser beam in a very, very quick succession at a very high frequency. You can modulate the laser beam. The laser beam is made to follow raster scan using a combination of mirrors, and then the intensity of the beam is modulated, and depending on the intensity the polymerization reaction will take place. So that is how this is the working principle of the resin based laser. Now for all these things to happen, you need a precision control of movement, and for that we make use of stepper motors. This is a little bit of engineering that comes into play, but I have tried to make it very, very easy for you to understand if just you know the basic physics of magnets, how they work. Will the audio play?
ऑलरेडी ऑन है. हेलो स्पीकर नहीं है. अच्छा यदि ऑडियो डायरेक्ट
there is no sound. There is audio link. It's नहीं आएगी because HDMI is connected, audio goes there.
नहीं सर ਇੱਥੇ भी ਆ ਜੀ.
नहीं आएगी. Okay, good. Let's make it full screen.
With such precision. It's all because of the stepper motor. What's special about the stepper motor is that
ऑन कर दो. स्पीकर लगाया नहीं सर.
they can control the angular position of the
I'll
motor
manage.
without
Just
closed
put all these things stuff on the side. नहीं चाहिए था कुछ.
and open loop system.
So stepper motor.
Let's first understand how the variable reluctance type of stepper motor works, which is the simplest one. Later on, we will move to a highly accurate and commonly used motor type. This motor has 6 stator teeth and can be energized with 3 separate DC power sources. rotor is made of a stack of steel laminations. It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. You can explain how this stepper motor works by yourself. If you de-energize coil A and energize B,
okay, I'll just explain it to you. What you have here is, you have 3 pairs of coils and the stator has got 4 teeth. Now when you energize one pair, that the corresponding tooth aligns with the coil and the motor moves one step. When you go beyond,
automated milling machine move with such precision. It's all because of the stepper motor. What's special about the stepper motor is that it can control the angular position.
right? So by adjusting the number of teeth in the rotor and the stator, the angle can be adjusted. All the commercial motors, as you are seeing in this printer, they all have a step size of 1.8 degrees because the magnetic poles of the rotor and the stator are designed that way. So you have 50 teeth on the rotor and 48 teeth on the stator, and their angular positions are so adjusted that when you energize one set of coils, then de-energize that and energize the next one, the motor turns by 1.8 degrees at a time. Then further resolution can be improved by making use of gears or pulleys, and you can get much finer resolution of movement. Another way of increasing the resolution is by using half stepping or micro stepping sequence. So अगर आप एक की बजाय 2 coils को energize करोगे तो rotor बीच में आके रुकेगा. So it will stop in between, and that way you can have half step. And if you continuously alter the magnetic field strength, the rotor will move slowly. Maybe you can have, like, instead of 2 you can have 4, 8, 16, 32 or maybe 64 or 128 or 256 microsteps in between. So that gives you very smooth and precise rotation. We call it as electronic gearing. So this is how the stepper is turning. This is full step. Then you can have half step. Now it will show you half step. So 2 coils will be energized simultaneously and the rotor will stop in between. So it is all based on the principle of least reluctance. So if you have done a little bit of physical chemistry or physics, you are aware about what reluctance is. It's basically concerning the path of the magnetic field. So this is how. Now the angle has been halved. This is half stepping. The actual motor will have much larger number of teeth. So as you will see in this video, this is the one. As you can see, this is a stepper motor here. A similar one. So it can give you a step size of 1.8 degrees. So these are all working usually in the open loop system. So you just pass on a certain number of pulses to the motor, and then it executes that many steps, and so that much angle it turns. So with that you can have a precise control over the movement, a digital control. So this is how it goes. Now next thing, what makes it all possible is the access to open source hardware microcontroller. So this one you're seeing here is an Arduino microcontroller. Then we have free and open source software. Ma'am, these are some of the packages that we use for 3D printing. So we have FreeCAD, as I've shown you. At the lower bottom corner we have OpenSCAD, that again is a free and open source software. And then on the top left you have PrintRun, that is for controlling the 3D printer. At the right side you have 3D Slicer, I'll show that to you. And in the lower bottom corner, bottom right is FreeCAD. Yes, please.
To illustrate how accessible it is, would you be able to say how expensive an Arduino board is?
They are all free and open source.
Yeah. No, but just to buy an Arduino board.
No, you don't need. They are like Wikipedia. They're crowdsourced.
Yeah, but the board itself, the hardware.
Hardware.
Does it cost an
Okay. The hardware can be open source but cannot be free.
Yeah, but how much?
This is Arduino Uno board. It costs around 500 rupees and around $10.
Yeah, so it's not.
It's not expensive. Then you have a bigger version, one is Arduino Mega, and that costs around 2 to 3 times this one, so around 1,500. So around $20-30. Mega is the one which is being used in this printer. And then you have other variants, Arduino Duo, that's double the cost but with much larger resources. So this is the symbol for open source hardware, and the other symbol is for open source software, this green one. Okay, then continuing with the journey, all of you know how the laser works. So this is something which is required for, like you see, if you have done a polymeric filling for your teeth, what they do perform a light cure. Have you seen that? A blue light, they place the tip on the, they first fill it with a liquid resin, then they place the blue light, and the light cure takes place in a matter of a few seconds. So the same way you can form solid components out of a liquid resin by having a very precisely located laser beam. It sweeps across the surface and the intensity is modulated. So that is the working principle of laser based printing. So I have two technologies, and we have these platforms for buying these things these days: Amazon, Gobu, RoboCraze, Electronics Comp, and so on. So 3D printing, when it came into being, it was used as a rapid prototyping option. 3D printers were very rare, they were very expensive. But with the passage of time, the entire process, it became much more user-friendly, it became much cost-effective, and the 3D printers, they became so common over the period of time that now you can stack multiple printers together to make a printing farm. You can control them using a centralized computer. You can have like 100, 200, 5,000 printers in a farm facility. Then you can just control what all parts are going to be made. So the amount of cycle time which a single printer takes to make parts, I've put it before you just to give you an idea. That cycle time is taken care of by having large number of printers working in parallel. Right? So that takes us to the manufacturing based on 3D printing. So now if you have to change a design, you don't need to go for fresh tooling, you can straight away go for it. Right? So these are the various processes: material jetting, binder jetting. I'll be quickly taking you through all this. So for material jetting, we'll play a video that will. It's just like your inkjet printer, but the thing is, the sheet onto which the printing is taking place is going down layer by layer, and fresh polymer is being layered onto it. So this is how the 3D printing is done. So in each pass, it throws some material onto it through the fine nozzles. 10 minutes और लगेंगे बस. So straight from the CAD model, just as you type a letter and then press Ctrl P here, same way you can do here. This is getting printed. There are many thousands of nozzles through which the material comes and gets deposited. Okay, I'll cut it short. Then we have binder jetting process. You will make use of powder particles, and binder is thrown in the form of certain patterns layer by layer, then a fresh layer of powder particles, then again binder, another layer of particles, and binder. So this process doesn't use liquid material, only the liquid binder is there. So it is used for making cores for the mold making process for foundry. So these kind of sculpts, if you want to make these sculptures, you can do a 3D printing first, then put that 3D printed component into a sand mold, then pour molten metal. The 3D printed plastic will simply evaporate and the metal will take shape in the mold. So this kind of complex shapes can be 3D printed using this process. So you have a pass of resin binder, then a pass of powder, again a pass of resin binder, and so on. Then this is ultrasonic sheet lamination, not actually 3D printing process, but here you can use metal sheets for, and they are welded, bonded together using ultrasonic horns. So layer by layer you can make the shape. So this is a sonot rod which is doing the bonding. Then using the laser sintering, we can have this powder bed fusion. So you have a layer of powder, then the laser fuses the powder particles at various locations. So layer by layer the process is completed. In principle this is very similar to resin printing, but this is using solid powder particles. Then we have photopolymerization. This has got probably the highest resolution among all the techniques, because the size of the pixel is decided by the cross section of the laser beam and the accuracy with which you can modulate. Dr. Hussain was just telling me that they have ordered a resin printer with a pixel size of 2 micrometers. It's very fine, but of course it will take very long cycle time to print one given component. So the laser beam is actually modulated with the help of liquid crystals. Then we have this FDM 3D printing as the one we are having here. You can see it on your own when you get up. So here's a video of that. The filament is fed from the above and is getting melted in this small cubicle head there, because it is got 40-watt heater. So the molten filament is pushed through a small nozzle. You can have different size nozzles. This one is 0.4 mm, and layer by layer the material gets deposited. So the printed components which I showed you, you can see they all have got layers. You can see on the side walls. They are done layer by layer. These are various geometries of FDM 3D printers. This one is following the Cartesian coordinate geometry, the one as you are seeing here on the table. Then we have delta printers. Did you watch the World Cup, no, not World Cup, this Champions Trophy match between India and New Zealand? On 9th, day before yesterday. Have you seen that camera which is suspended in the playground? It's following the same delta geometry. So using 3 ties, it can be taken to any location over the field. So this is the delta based geometry. So we have a vast choice of materials. You can see one black colored roll here. So you can have multicolored, multi-material rolls. Dozens of types of materials available, each for their own application. Then we have various parameters like what kind of polymer blend, what color, some of the attributes. Then the parameters can be divided into various broad categories. One is concerning the material category, then the printer settings, how much infill you want, how many surface layers you need. what is the pitch, the layer height kind of resolution. So some settings are pertaining to the printer, some settings are pertaining to the material, and some settings are pertaining to the printing process. So you have to just choose the best combination that gives you the desired result in terms of speed and accuracy. And you can make some customized parts. So it's a watch, wristwatch strap with name printed onto it. So then you can make parts which are not available in the market. I wanted to precisely control my telescope, so the brackets were not available, so I 3D printed them, right, to do the required job. Then you can have some impossible assemblies or components. Like here you have got a nut, but the screw is having caps on both the sides. So it's not possible to have something like this in the conventional process. एक तरफ से चूड़ी चढ़ा होगी उसकी, तो एक साइड खुली होनी चाहिए, right? But here you can, because you're printing the assembly itself, so you can have nut made layer by layer onto the bolt. Then these are some of the advantages of 3D printing. Here again you have got an impossible assembly. Then talking about the technology readiness levels, 3D printing is already at the TRL 9. So it can perform all the required operations that we need to have in place. So if human race is to colonize other planets, 3D printing is going to be first and foremost thing to be deployed onto those platforms. So coming to the limitations and drawbacks, there are some technological aspects like speed, for example, and choice of materials. Another, in metals also, metal 3D printing has become possible. It is somewhat limited. Then coming to legal aspects, there have been instances when individuals have printed weapons using 3D printers, and those weapons, they can be printed at any place and then destroyed. So you can have a 3D printed pistol, maybe you can commit a crime and then destroy. And the worst thing is it doesn't leave any signature on the bullet marks. So that's the legal aspect. Then some of the recent landmarks, 3D printing of an entire engine, right? And L&T construction, it 3D printed a building. You can watch a video on YouTube. Then the future is concerning flexible and smart 3D printing from flexibles in terms of flexible manufacturing system, where they can take up a mix of product, a variable mix of products, what to make. Then of course, as I said, 3D printing farms on Moon and Mars. So by the time you go there, you have the things ready. And then 4D printing is something which makes parts which change shape with time. That's a fourth dimension. So that's all from my side. If you have any questions, welcome to ask. Thank you. It is also finished. Yes.
So we have a lot of students here in the room that are working on the development of new materials. Do you have the capability to make your own filaments so that once they've made a material in the lab, they may be able to 3D print something to test if their
Yes, certainly that can be done. You just need a small extrusion type of machine which can also be made like DIY. Because the materials are not certainly going to be in large bulk. It's going to be small quantities. So we can make a filament of our own. The only thing is you just need to exercise some control of the diameter and the homogeneity. That's it.
So for those of you that are working on material-based projects,
that's very nice.
Think outside the box.
You can start working on materials, because all these materials that we are seeing around, they have also been developed by somebody. So you can extrude them into the form of a small filament and then wind it onto a roll and then use in a printer. That's a wonderful thing to do. Any other questions before we part for tea? Thanks for joining. After this, we'll have a hands-on experience on FDM 3D printing. That's why I've brought the printer here, and I'll take you through various steps of from modeling to printing. Right? Are you excited or not?
Yes,
Doesn't seem to be so. Thank you.
engineering isn't scary. You just have to jump into it.
Yes.
It is very hands-on. Everybody played in a sandpit as a child.
Take it as a toy.
This is the new
You can
sandpit.
experiment with. And this is not something which has been brought for an exorbitant cost, and if something goes wrong, I'll not be able to repair it. It's all homegrown during the lockdown. So nothing can go wrong with it.
Well, if it goes wrong, you just go again.
Yeah, we can just
Fail
repair.
fast, fail.
Yes, yes. So with that, I think we should close, and then we'll come back for the hands-on training.
I think that their training will be much better.
Hmm?
The training will she asked if they're
Yeah, training on this one. Yes, yes. You will try hard.
Try.
तोड़ दो इसको, तोड़ के दिखाओ।
रीस्टोर नहीं, इट इज बेसिकली द काइंड ऑफ
ये खराब ही नहीं होगा।
काइंड ऑफ मटेरियल जो उन्होंने
हीट से इफेक्ट होता है। तो वर्किंग टेम्परेचर हम नॉर्मली इसका जो 27 पे इसकी प्रिंटिंग होती है, तो 100 डिग्री तक कोई फर्क नहीं पड़ता। नो, एम्बिएंट एयर इज एट अराउंड 20-30 डिग्रीज।
जब हम यूज करते हैं ना, मतलब हमारा जो कंप्यूटर में यूज करते हैं, कभी कभार हम ऐसे सॉफ्टवेयर यूज करते हैं जिससे हमारा मतलब सीपीयू ओवरहीट हो जाता है, तब
तो सीपीयू नहीं ना, ये तो आपका RJ45 दीवार पे लगना, वो तो गर्म ही नहीं होना।
उसमें तो हीटिंग
अगर धूप नहीं पड़ेगी तो 60-70 पे पहुंच जाएगा। 67 डिग्रीज इज ओके, गुड। हाँ, PLA में द लिमिटेड वर्किंग टेम्परेचर 60 डिग्री सेल्सियस, बिकॉज उसके बाद ये डिफॉर्म होना शुरू हो जाएगा। इट्स अ थर्मोप्लास्टिक एनीवे, राइट? दिस इज आल्सो थर्मोप्लास्टिक, बट इसका जो ऑपरेटिंग टेम्परेचर
ये क्या मटेरियल है सर? ये
दिस इज TPU, दिस इज ट्रांसपेरेंट TPU, दिस इज ब्लैक TPU, thermoplastic polyurethane.
ओके,
This is one of the toughest materials, challenging to handle also in the printer. Not every printer can print in TPU. Even to me, it took a couple of years before I could start printing in TPU.
सर जैसे आपने वो ट्रैक्टर वाला एग्जांपल दिया था, उनके पार्ट्स तो काफी बड़े होते हैं, तो ये जो ऑब्जेक्ट हम प्रिंट करते हैं इनके भी साइज का कोई
नहीं, बड़ा printer बन सकता है।
ओके
सर वो तो आपने बताया था कि हम पाउडर मटेरियल यूज करते हैं,
हाँ।
तो उस पाउडर मटेरियल के अल्टरनेटिव कोई चीज यूज करना चाहते हो, क्या कर सकते हैं?
नहीं, ऐसा है 3D प्रिंटिंग के बहुत सारे आपके पास टेक्नोलॉजीज हैं। पाउडर इज वन, रेजिन इज अनदर, रेजोल्यूशन कितना है। अब मैं आपको सिंपल एक चीज़ बताऊं, कई बार तो आपको होता है लाइक यू वांट टू डू इन्वेस्टमेंट कास्टिंग, सो यू वांट टू यूज अ मटेरियल। इन्वेस्टमेंट कास्टिंग क्या है? बेसिकली आपने एक कंपोनेंट जो आपको चाहिए, जैसे ये मूर्ति आपने बनानी है, अब आपने इसको बनाना ब्रास में, तो ब्रास में तो आप इसकी स्कल्पटिंग नहीं कर सकते। आप क्या करोगे? आप किसी सॉफ्ट मटेरियल में, मे बी वुड में आपने वो स्कल्पटिंग कर ली, या वैक्स में कर ली। मोस्टली वैक्स से करती है इन्वेस्टमेंट कास्टिंग प्रोसेस हम बोलते हैं। तो वैक्स की बना ली प्रिसाइजली, वो सॉफ्ट है बना ली। अब वैक्स को आपने सैंड के मोल्ड में रख के उसमें सैंड डाल दिया, राइट? सैंड इज देयर, वो उसकी सारी शेप ले लेगा, राइट? नाउ वंस दैट इज डन, उसके बाद आपने उसको ड्राई होने दिया, सैंड सेट हो गया आपका। सीमेंट नहीं डालना, सिर्फ सैंड ही है वो, उसमें थोड़े से एडिटिव्स हैं, मोलेसिस वगैरह होते हैं सैंड में, बाइंडर्स होते हैं, सीमेंट नहीं है, बिकॉज नहीं वो क्रैक करेगा बाद में। तो वंस दैट इज सेट, अब मोल्ड सूख गया, आपको ओवरनाइट उसको रख दिया, फिर आप उस मोल्ड को ओवन में हीट करते हो। जब हीट करोगे तो जो वैक्स है वो मेल्ट होके बाहर निकल जाएगा। अब क्या है? उसकी शेप की एम्प्टी कैविटी बन गई। अब आप ऊपर से मोल्टेन मेटल उसमें पोर करोगे, वो उसमें शेप ले लेगा। जो बीच में एयर है, बिकॉज सैंड इज पोरस एंड परमिएबल, सो एयर विल एस्केप थ्रू द वेंट्स एंड मेटल विल टेक द शेप। हाँ, हल्का फुल्का आपको इसकी फिनिशिंग करनी पड़ेगी, बिकॉज वो सैंड पार्टिकल्स की वजह से थोड़ा सा कोर्स होगा इसका सरफेस, तो आपने वो फिनिशिंग करनी है एमरी पेपर से, सो स्कल्पटिंग इज डन। दिस इज वन प्रोसेस। अनदर प्रोसेस इज लाइक यू हैव थर्मोकोल, जैसे यहाँ पे लगा हुआ ये स्टायरोफोम। तो आपने अगर कोई बड़ी मोल्डिंग्स बनानी है, यू मेक द शेप आउट ऑफ थर्मोकोल, अ ह्यूज वन, राइट? अब थर्मोकोल, इफ यू अप्लाई हीट टू इट, इट सिंपली सब्लिमेट्स, श्रिंक करके इतना सा रह जाएगा। तो आपने इन्वेस्टमेंट मोल्ड बनाया, उसमें थर्मोकोल डाला, कुछ नहीं निकालना, कुछ नहीं सुखाना, नो ओवन, नथिंग, जस्ट पोर द मेटल। As the metal progresses, metal is very hot and heavy, so it will push the thermocol and it will simply give way, and you will get a replica of the shape that you made in thermocol. All these are the formative processes. ठीक है? तो ये कास्टिंग हम इसको बोलते हैं, और the industry is known as foundry industry. मोल्डिंग मटेरियल्स के साथ अब प्रिसीजन कंपोनेंट्स बनाने हैं, देन वी हैव प्लास्टिक इंजेक्शन मोल्डिंग प्रोसेसेस। ये कंप्यूटर माउस, ये सब, ये मोबाइल, इसके कंपोनेंट्स, जितने भी आपको प्लास्टिक कंपोनेंट्स यहाँ पे दिख रहे हैं अपने आसपास, ये बॉटल, इसका ढक्कन, मोस्ट ऑफ देम हैव बीन मेड थ्रू द प्रोसेस ऑफ इंजेक्शन मोल्डिंग। द ओनली थिंग इज, द डिफरेंस हियर इज कि अब आपका मोल्ड सैंड का नहीं है, इट्स अ मेटालिक मोल्ड। आपने CNC मशीन के साथ प्रिसाइजली वो कैविटी बना दी। ये प्रोजेक्टर की बॉडी देखिए आप, तो पहले आपने मेटल, ये सारी हाउसिंग, इसका नेगेटिव रेप्लिका बना दिया, ठीक है? तो एक कंपोनेंट ऐसा है, दूसरा उसके बीच में होगा। थिन वॉल्ड आपको चाहिए ना, सॉलिड तो बनाना नहीं, प्लास्टिक बीच में खाली भी चाहिए। तो ऐसे दो कंपोनेंट्स होंगे, बीच में एक जगह से प्लास्टिक एंटर करेगा और अपोजिट साइड से एयर एस्केप करेगी, ठीक है? तो इन अ फ्रैक्शन ऑफ अ सेकंड वो सारा प्लास्टिक से फेल हो जाएगा। देन यू हैव कूलिंग वाटर गैलरीज, जो उसको थोड़ा ठंडा करेंगी, मे बी अ कपल ऑफ सेकंड्स और सो। तो टेम्परेचर को एडजस्ट करना है कि प्लास्टिक कितने टेम्परेचर पे आएगा और मोल्ड का कितना टेम्परेचर आपने रखना है। ये ना हो कि आपको ठंडा करने के लिए टू वेट फॉर 15 मिनट्स, सेट द टेम्परेचर अकॉर्डिंगली, राइट। सो यूजुअली क्या करते हैं, अगर इसमें एक मोल्ड है, बड़ा पार्ट है, तो एक मोल्ड में एक्सीडेंट एक निकलेगा। सो यूजुअली वी लाइक सेट द पैरामीटर्स ताकि लगभग 1 या 2 सेकंड में एक कंपोनेंट बन के निकल जाए। तो 1 घंटे में 1800, दिस इज मास प्रोडक्शन। सीडी के जूल केसेस देखे आपने, ऐसे खुला कर कॉम्पैक्ट डिस्क के जूल केसेस। आई हैव सीन एट प्लास्टिक इंडिया शो होता है दिल्ली में, प्रगति मैदान में। आई हैड सीन अ मोल्ड मेकिंग मशीन प्रिंटिंग द जूल केसेस फॉर द कॉम्पैक्ट डिस्क, 4 at a time, mold closing and opening every 1 second. So the production rate in a single mold was 4 jewel cases in a second. मतलब वो इंजेक्शन ओपनिंग, मतलब क्लोजिंग, इंजेक्शन ओपनिंग, इंजेक्शन अगेन क्लोजिंग, अगेन इंजेक्शन, इट सिंपली रेप्लिकेट्स। दैट्स द इंडस्ट्रियल प्रोसेस। हाँ, व्हेन यू हैव टू एस्टैब्लिश द प्रोसेस यू हैव टू फॉलो सम इटरेशंस, 2, 4, 6, 8, 10, 1 दिन, 2 दिन, 3 दिन आपको पैरामीटर्स ट्यून करने में जाएंगे। बट वंस द पैरामीटर्स हैव बीन ट्यून्ड, द प्रोसेसेस कैन बी लेफ्ट अनअटेंडेड। The only thing you need is a precise control over the parameters and a precise homogeneity of the material. Just as here, this filament is very homogeneous. If the melting point changes from place to place, this printing will fail. If the diameter changes from place to place, it will get stuck. कहीं पे inadequate आएगा, पतला हो गया, sufficient material नहीं है ना। तो properties और इसका जो physical form है, geometry, that should remain consistent.
जो हार्डवेयर सॉफ्टवेयर इंटरफेस है,
हाँ,
वो कैसे एस्टैब्लिश?
हाँ, वो मैं आपको
मतलब
नहीं आपको सारा दिखा दूँ। स्टेपर मोटर की वर्किंग तो आपने देख ली थी, मैग्नेटिक पोल्स कैसे उसको थोड़ा थोड़ा घुमाते हैं, ठीक है। सो ये इसमें देखो स्टेपर मोटर्स, ये 2 नीचे लगी हैं, दीज आर फॉर द जेड एक्सिस। इनसे ये लीड स्क्रू घूमेगा और ये पूरी की पूरी क्रॉस बार है जो ये ऊपर नीचे जाएगी, ठीक है। दिस इज जेड एक्सिस। देन फॉर एक्स एक्सिस ये वाली मोटर है और ये इसको ऐसे हिलाएगी बेल्ट के साथ, ठीक है। फॉर वाई एक्सिस द बेड मूव्स, राइट। अब इनको आपस में कोऑर्डिनेट करना है, वो माइक्रो कंट्रोलर करेगा। यू हैव टू गो अपस्टेयर्स। आप लोग इधर आइए। हाँ बताइए।
It's like a CD system.
लाइक
CD system when we use a DVD.
उसमें भी स्टेपर मोटर नहीं है। हाँ बिल्कुल।
सर ऊपर आना है?
हाँ ऊपर आ जाओ, आपको यहाँ माइक्रो कंट्रोलर दिखा रहे हैं इसका। ये इसका कंट्रोलर बोर्ड है, इसके नीचे लगा ब्लू रंग का आर्डिनो, दिख रहा है साइड से, ऊपर तो कनेक्शन शील्ड है,
ब्लू कलर का दिख रहा है।
हाँ नीचे दिख रहा है, इधर देखो आपको, इधर सेंटर वाला पोर्ट भी दिखेगा उस पर, इधर देखो ये पोर्ट दिख रहा है ना, वो नीचे ब्लू कलर का बोर्ड है, दैट्स आर्डिनो मेगा बोर्ड। ओके ठीक है, तो 1000-1200 रुपए का। ये ऊपर शील्ड लगी है, दिस इज ऑल रेडीमेड अवेलेबल, दिस इज नोन एज रैम्प्स 4.0 शील्ड, आपको अमेज़न पे 400-450 रुपए की मिल जाएगी।
कौन सी शील्ड?
ये जो रेड कलर की है ये सारी।
ओके ओके
ठीक है, और इसमें स्टेपर मोटर के माइक्रो स्टेपर्स लगे हैं, ये 2 3 4, ठीक है। एक 5वें की स्पेस है खाली, 5 लगे हैं, 5 है। तो वन इज फॉर एक्स, एंड दिस फॉर वाई, अनदर इज फॉर जेड। एक है उसमें जो आपके एक्सट्रूजर, ये जो एक्सट्रूजन कर रहा है ना, यहाँ पे स्टेपर मोटर लगी है ये वाली, जो फिलामेंट को फीड करती है, ठीक है। एक उसका है, एक स्पेयर है। एक्चुअली इसमें 2 एक्सट्रूड लगने की व्यवस्था है, आप एक मोटर यहाँ पे भी लगा सकते हो। इफ यू वांट टू लाइक हैव 2 फिलामेंट्स फीडिंग, तो एक मैंने लाइक मल्टी लेयर करना है, एक येलो कलर में करना है, एक ब्लैक में करना है, एक हार्ड का करना है, एक सॉफ्ट का करना है, सो दैट कैन बी डन।
तो दो को एक साथ चला सकते हैं।
हाँ, 2 एक साथ चलाने की है, बट वो किया नहीं मैंने, बिकॉज इट मेक्स द होल थिंग मोर कॉम्प्लिकेटेड। ठीक है, टाइम भी नहीं मिला, कभी कर सकते हैं, राइट। ये हो गया, फिर इसमें
होल बॉक्सेस, इसको होल बॉक्स को
ये इसका कंट्रोलर है,
कंट्रोलर
है।
ओके,
वो कोई महंगा नहीं है, कुछ नहीं है इसमें। इफ समथिंग गोज रॉन्ग, वी कैन, इट्स अ मॉड्यूलर डिजाइन। माइक्रो कंट्रोलर खराब हो गया, इसको निकालोगे, नया लगाओगे, उसे प्रोग्राम उसमें ट्रांसफर कर दोगे, दैट्स इट, नथिंग टू वरी, है ना। हाँ, अगर आप इफ यू गो फॉर रेडीमेड आइटम फ्रॉम द मार्केट, then everything becomes much more expensive. Replacement parts are much more expensive. So this is homegrown, तो इसमें कोई issue नहीं है. अब पता चल गया आपको कि ये मोटर्स यहाँ से कंट्रोल हो रही हैं, राइट? और इसका प्रोग्राम भी इसी में लोड होता है. पर प्रोग्राम डालते यहाँ पे है. ये डला आपका मेमोरी कार्ड, ठीक है, माइक्रो एसडी अडेप्टर में डला और ये हो गया. सो दिस आई कैन पुट इनटू द लैपटॉप, लोड द प्रोग्राम, देन पुट इट हियर एंड देन. तो लैपटॉप को एंगेज, चाहो तो आप लैपटॉप को यहाँ पे केबल से भी कनेक्ट करके प्रोग्राम लाइव चला सकते हैं, बट देन योर लैपटॉप मींस एंगेज्ड ऑल द वे. अगर 3 घंटे प्रिंटिंग हुई है, 3 घंटे लैपटॉप रखना पड़ेगा साथ में. सो दिस डीकपल्स, तो प्रिंटर स्टैंड लोन बन गया. प्रोग्राम कॉपी किया, इसमें डाल दिया और चल सकता है. ठीक है, गेटिंग कंफर्टेबल ना?
Yes, sir.
तो ये जस्ट कूलिंग फैन है, बिकॉज जब मोटर्स चलती हैं तो ये हीट जनरेट होती है. इसको ठंडा करने के लिए ये एग्जॉस्ट फैन है ऊपर, इधर से हवा जाएगी, इसको ठंडा करेगा. सिंपल, नो रॉकेट साइंस. ठीक है. पावर सप्लाई के नीचे ये यूपीएस लगा जो कंप्यूटर में लगता है. एवरी डैम थिंग इज अवेलेबल इन द मार्केट. घर पे वेस्ट पड़ी प्लाईबोर्ड को सनमाइका लगा के ऊपर लगा दिया, तभी पूरे साइज की नहीं है, बिकॉज जस्ट यूज द वेस्ट. ठीक है, लॉकडाउन में किया ना, तो वट एवर मटीरियल वाज अवेलेबल एट होम तो उसको यूज कर लिया. क्लियर? एंड टू बिगिन विद ये सारे कंपोनेंट्स ऐसे टेबल पे बिखरे पड़े थे, तो जो ये कंपोनेंट्स हैं वो इसी में 3D प्रिंट हुए हैं, जो येलो में आपको देख रहे हैं सारे. तो धीरे धीरे इसने अपनी बॉडी को खुद ही बना लिया. ट्रांसफॉर्मर्स वो देखिए ना, वो भी अपने आप को खुद ही बना रहा है. तो वो चीज़ है. गॉट इट? ये कुछ कंपोनेंट्स हैं जो मैंने स्टील में फैब्रिकेट कराए हैं, लेकिन इसके बाद डिपार्टमेंट में मैंने बच्चों को प्रिंटर बनवाया, वो पार्ट भी हमने 3D प्रिंट कर लिए थे. इसमें प्रिंटर
स्टील में ही सर
ना, प्लास्टिक के पार्ट्स ज़्यादातर यूज़ के लिए, कुछ स्टैंडर्ड यूज़ कर लिए. रॉड्स वगैरह तो मिल जाती है मार्केट से, अमेज़न से मिल गई. उनके होल्डर्स वगैरह, जैसे ये ब्रैकेट्स, ये स्टील की हैं, ये एल्युमिनियम की ब्रैकेट्स हैं, ये हमने प्लास्टिक की बना ली. इतना लोड तो इन पे है नहीं. इवन यहाँ पे ना, ये देखो यहाँ पे ना, ये लगते हैं आपके चैनल के नट्स, वो भी हमने 3D प्रिंट किया, बिकॉज ये बहुत एक्सपेंसिव बेचते हैं. ये देखो यहाँ पे ना, ये नट्स हैं, ये 16 रुपए का एक है. बट व्हेन यू हैव अ प्रिंटर तो आप अपने बना सकते हो. इसमें यहाँ हेक्स कटा हुआ, इसमें रेगुलर नट जो 60 पैसे का है वो इसमें चला जाता है, और ये आपका आराम से इस चैनल में स्लाइड कर जाएगा. बिकॉज ये बहुत सारे यूज होते हैं, तो 200 लग जाते हैं ऐसे, तो 200-16 रुपए के दे बिकम सब्सटेंशियल. तो ये सस्ते में बना लोगे. ये मैडम सारी माउंटेन्स, ये इसको आपस में ज्वाइन करने के लिए.
अच्छा.
ये तो बल्क में यूज होते हैं. तो जब हमने डिपार्टमेंट में बनाना था, वी डिडंट हैव अ प्रोजेक्ट मनी, पॉकेट से बनाना था. सो वी डिड ऑल दिस कि अपने बनाओ, अपने करो, और बच्चों ने उसमें ट्रेनिंग ले ली. ठीक है ना. इवन ये चैनल फिर ये शार्प होते हैं एजेस, तो इसके लिए कवर ये भी खुद ही डिज़ाइन करके प्रिंट किया है. किसी को
इसमें ऑटोकैड भी यूज कर सकते हैं.
ऑटोकैड इज बेसिकली फॉर 2D ड्राफ्टिंग, उसमें 3D मॉडलिंग का नहीं है. एंड देन ऑटोकैड इज अ पेड सॉफ्टवेयर, इट्स अ प्रोप्राइटरी.
लास्ट वीक में यूज किया था, उसमें मतलब भी अपडेट है, उसमें 3D प्रिंटिंग हो
लिमिटेड सा है. एक्चुअली ऑटोकैड का जो DWG फॉर्मेट है ना अजय, वो DWG फॉर्मेट इज एक्चुअली नॉट अनेबल्ड फॉर 3D मॉडलिंग. ऑटोकैड में AME आती थी हमारे टाइम पे, वे बैक इन 1995 जब मैंने यूज़ करना शुरू किया 94-95 में. इट यूज्ड टू बी टर्म्ड एज एडवांस्ड मॉडलिंग एक्सटेंशंस, पर उसमें पैरामीट्रिक मॉडलिंग नहीं थी. आजकल पैरामीट्रिक सॉफ्टवेयर यूज हो रहे हैं. देन FreeCAD इज गुड गो गेटर. इट्स नॉट द मोस्ट पावरफुल सॉफ्टवेयर आउट देयर, बट इज फ्री.
डिजाइन कर सकते हैं,
ठीक ठाक काम कर सकता है. थोड़ी सी उसकी वीकनेसेस हैं. एज यू वर्क यू रियलाइज हाउ टू लाइक उसके वर्कअराउंड्स के, उन वीकनेसेस के. एंड एवरी अदर डे इट हैज अ न्यू वर्जन बिकॉज इट्स क्राउड सोर्स्ड. तो उसके मॉड्यूल्स लोग बना के उसमें असेंबल कर देते हैं. तो आप यू कैन डाउनलोड एनी नंबर ऑफ मॉड्यूल्स. जैसे आप सपोज पावर पॉइंट में अपनी प्रेजेंटेशन बनानी है, तो जो माइक्रोसॉफ्ट आपको दे रहा है वही है. बट अगर आप क्लाउड बेस्ड प्रेजेंटेशन बनाओगे, गूगल कैनवा पे बना रहे हो, तो आपको n नंबर ऑफ उसमें थीम्स ऑप्शंस मिल जाएंगी, लोगों ने डाले हुए हैं. विकिपीडिया पे आर्टिकल आप भी लिख के डाल सकते हो, है ना. ऑक्सफोर्ड में नहीं जाएगा. तो ये फर्क है. दिस इज ऑल क्राउड सोर्स्ड, इसलिए किसी एक की प्रॉपर्टी नहीं है, तो इसमें रॉयल्टी नहीं है. ठीक है. अगर आप इसके साथ कमर्शियल काम भी करोगे तो इलीगल नहीं होगा. ऑटोकैड में अगर आप ड्राइंग बना के बेचते हो इट्स अ कमर्शियल एक्टिविटी, यू कैन बी सूड, बट इसमें फ्री कैड में नहीं है, ओपन एस कैड भी ऐसे ही है, ठीक है। तो अब सबसे पहले तो थोड़ी सी आपको पार्ट मॉडलिंग सीखनी पड़ेगी कि है क्या बना वो, है ना, कैड मॉडलिंग करते कैसे हैं। कैड मॉडलिंग के बाद आएगा आपने मॉडल से प्रोग्राम जनरेट करना है, ज्योमेट्री आपने डिफाइन कर ली, बट इसका हेड को उसके ऊपर लेके जाने के लिए एक प्रोग्राम बनेगा ना, है ना, टेक्स्ट फॉर्म में फाइल होती है वो, यस, मूवमेंट डिफाइन करने के लिए, ठीक है, वो प्रोग्राम, वो सारा काम कंप्यूटर में होगा। वंस यू हैव दैट प्रोग्राम रेडी, फिर आप प्रोग्राम इसमें लोड करोगे यहाँ पे। अब उस प्रोग्राम को लाइन बाय लाइन इंटरप्रेट करके मोटर्स को कमांड देनी है, उसके लिए एक अलग सॉफ्टवेयर है, दैट अगेन इज एन फ्री एंड ओपन सोर्स एंड कस्टमाइजेबल सॉफ्टवेयर, मेर्लिन आपको मिल जाएगा। तो मेर्लिन आप लैपटॉप में डाउनलोड करोगे, कंप्यूटर में डाउनलोड करोगे, उसको प्रिंटर के हिसाब से कस्टमाइज करोगे, ओके मेरी मोटर कितने स्टेप में कितनी मूवमेंट है, वो शुरू में मेजर करनी पड़ती है, कितनी बड़ी पुल्ली लगाई है तो बेड कितना मूव करेगा एक स्टेप में, ऑल दोज थिंग्स। तो वो पैरामीटर आप उसमें प्रोग्राम में सेट करते हो, फिर आप कैलिब्रेशन क्यूब्स वगैरह प्रिंट करते हो, नापते हो वर्नियर से, हाँ ठीक है, पैरामीटर सेट हो गए, देन यू स्टार्ट, फिर आपकी प्रोडक्शन वाला काम शुरू हो जाएगा। तो वो सारा है एंड टू एंड प्रोसेस। सो फर्स्ट यू नीड अ कैड सॉफ्टवेयर, कैड सॉफ्टवेयर से आप एसटीएल फाइल एक्सपोर्ट करोगे, देन यू नीड अ सॉफ्टवेयर विच कैन इंटरप्रेट द एसटीएल फाइल
इन टेक्स्ट फाइल।
हाँ, नहीं, एसटीएल इज बेसिकली ज्योमेट्री फाइल, ट्रायंगल्स होती हैं उसमें, सारे सर्फेसेस ट्रायंगल से दिखाई हैं, तो ट्रायंगल्स को रीड करके वो उसमें आपको लेयर बाय लेयर उसको स्लाइसिंग करके और लेआउट बनाएगा। उसमें आप प्रिंटर के पैरामीटर उसको बताओगे, मेरी नोजल कितनी मोटी है, लेयर हाइट कितनी रखनी है, स्टेप साइज वगैरह कितना, वो प्रिंटर के पैरामीटर के हिसाब से प्रोग्राम बना देगा। नाउ व्हेन द प्रोग्राम इज डन, आप उसके इसमें लोड करोगे, थर्ड सॉफ्टवेयर उसको रन करेगा रियल टाइम में, बस दैट्स इट।
प्रोग्रामिंग का सॉफ्टवेयर वो अलग है,
एक डिजाइनिंग का हो गया,
प्रोग्रामिंग
एक डिजाइनिंग का,
एक कैड हो गया,
एक प्रोग्राम बनाने का, एक प्रोग्राम को रीड करने का,
ओके,
तीन है,
3 सॉफ्टवेयर हो गए टोटल,
ठीक है। तो ये तो आप किसी भी कैड सॉफ्टवेयर में मॉडल बना सकते हो। एसटीएल इज अ न्यूट्रल फॉर्मेट, सारे सॉफ्टवेयर से एसटीएल एक्सपोर्ट होता है, जैसे वर्ड से आरटीएफ फाइल एक्सपोर्ट कर सकते हो, टेक्स्ट फाइल लिख सकते हो, एसटीएल फाइल आप हाथ से भी बना सकते हो टाइप करके। अगर आपको सिंपल ज्योमेट्रिक क्यूब बनाना है तो आप उसमें कोऑर्डिनेट स्पेसिफाई करके क्यूब्स बना सकते हो एसटीएल, बट कॉम्प्लेक्स शेप्स के लिए ऑफ कोर्स बहुत बड़ी एसटीएल फाइल बनेगी, वो सॉफ्टवेयर करते हैं, ठीक है। सीएनसी प्रोग्राम आल्सो यू कैन राइट बाय हैंड, कमांड ही देनी है ना, अगर सीधी लाइन ही मारनी है, ऐसे एक स्क्वायर बनाना है तो आप हाथ से प्रोग्राम लिख के बना सकते हो, बट अगर आपने कॉम्प्लेक्स शेप से ऐसे गोल करना, अंदर जाना बाहर जाना, फिर ऐसे ऐसे जिगजैग में उसको फिल करना है, वो प्रोग्राम लंबा होगा, अभी आपका दिखाया था प्रोग्राम, ठीक है।
हाँ, एक
वो सॉफ्टवेयर
जैसे आपने ये रिंग ही बनाया है,
नहीं हम अभी सारे करते हैं,
हाँ।
आ जाओ नीचे कॉपी चले, उधर देखना सही रहेगा, मॉडलिंग तो वहीं पे देख लो ना। वो वाली राइट सेकंड भी बंद कर दें, फिर आप उठ के आ जाना इधर। तो दिस फ्री कैड तो आप यू कैन राइट अवे गो बैक टू प्लेसेस एंड इंस्टॉल। आपको लैपटॉप चाहिए होगा विद द ग्राफिक प्रोसेसर, नहीं तो परफॉर्मेंस
डाउनलोड करना पड़ेगा,
सॉफ्टवेयर डाउनलोड करोगे, पर लैपटॉप में हार्डवेयर में मतलब अगर ग्राफिक्स वाला लैपटॉप है तो बेटर है। ओके, ये वाली बंद कर दो राजी, ये वाली, हाँ बस ठीक है। अभी जैसा हमने पार्ट बनाया था मैं आपको अभी वो दिखाता हूँ, इसको फाइल को कर देता हूँ। दिस इज फ्री कैड इंटरफेस, अभी खुल रहा है। We can go for a new file.
ये डाइस आता है आगे।
अच्छा, I think I'm obstructing your view, is it?
नहीं सर, it's okay.
Okay. You tell it to make a new body. Okay, we have to select a sketch plane. आप लोग imagine करो any irregular shape. Think of an irregular shape. Any irregular shape. बोलो. It's not written in a notebook. Any irregular shape. Potato. Cloud. Ginger. Cauliflower. All these are irregular shapes. A potato, for example, if you cut a section without peeling it off, the peel will form a boundary,
Yes, sir.
right? And the boundary will it be an open boundary or a closed boundary?
Close boundary.
जो छिलका होगा पोटैटो का, if you आपने कट कर दिया उसको, कट कर दिया, look at the peel. You start from one location, go around the periphery. Peel को देखते देखते, do you come back to the starting point? Yes? That means the boundary is closed. Can you think of a solid which when you cut has an open boundary? No. Solids are characterized by a closed boundary. Right? So whenever you section a solid, the boundary is bound to be closed. You can certainly have a boundary within a boundary. If you have something like a donut, you cut the donut in half. You will have one closed boundary here, another closed boundary here. So you will have two islands, two closed boundaries. Or maybe you can have, if you cut the donut along the middle section, not like this but this way, along the horizontal axis, along the horizontal plane, right? Then you will have an outer boundary and an inner boundary. So one boundary will be completely enclosed in another, or both will be closed. If you cut it like this, both boundaries will be closed in themselves. So you can have multiple closed boundaries, some lying entirely inside the other. You can never have closed boundaries which are intersecting, because they'll become something like this. Basic logic understand हो गया अब? Now that means अगर हमें solid को काटते हैं तो you get closed boundaries. तो अगर solid बनाना है we'll have to start with closed boundaries, closed sections. पहला सेक्शन है ये CAD का, और हर एक सेक्शन पे एक प्लेन चाहिए होगा कोई ना कोई. So I just pick up this XY plane, or I can start in any of the planes I need, I wish, right? Okay. अब यहाँ पे हमारे पास टूल्स हैं. यू कैन यूज़ पॉलीलाइन, अ लाइन और वट एवर. तो हम एक शेप बनाते हैं सिंपल सी. ये सॉफ्टवेयर ऑटोमेटिकली देखो ये साथ में कंस्ट्रेंट्स आ रहे हैं. ये देखो हॉरिजॉन्टल, इट विल ऑटोमेटिकली मेक माई लाइन हॉरिजॉन्टल, वर्टिकल, ये देखो हॉरिजॉन्टल, वर्टिकल, तो हाथ से पॉइंट ऑन पॉइंट. ओके, I can add or remove constraints as I wish. So यहाँ पे constraints हैं आपके पास. So you can tell it, it's a new version, the interface has changed a bit. Horizontal, vertical, okay. So constraint horizontal. So I click on this line, it becomes horizontal.
Okay.
Easy?
कुछ curve बनाना हो?
बना सकते हैं. You can have circles, arcs.
Okay.
ये देखो.
It is worth spending an afternoon or a day playing around with the software.
Yeah, you can just download, and n number of YouTube videos are available. I'm just giving you a
This is
start.
very hard to learn from
Yes,
seeing.
yes, yes.
It is something you just need to invest some time.
We are constrained on time. We have to finish in a 30 minutes period maybe, right? So I'll just give you a starter here, and then you can do. Okay, then you have the other constraint is point on curve, or you can specify your dimension. Okay, I pick the point. It's very intuitive. You click on the line. Okay, click here. How much distance even? Okay, 1 mm. Then just click on the line and click somewhere. Okay, make it 2 mm. Click on a point. Click here. Okay, let's make it 12. click on the line, click here, make it 1.5 mm. And एक आपको साथ में दिखाएगा 2 DUF. It means 2 degrees of freedom are still remaining. Let me just do one thing for you. Let's delete the sketch. Let's delete everything. Okay, let's say we draw a circle. Now, right now, neither the location of the circle is defined nor its radius is defined.
Yes.
So you need to define the horizontal location, the vertical location, and the size of the circle. So how many degrees of freedom are left? 3.
3.
X location, Y location, and size, radius or diameter. Either one of them will control the other. So it is showing you under constraint 3 DUFs. DUF stands for degrees of freedom. Okay, let's say you specify one dimension. So I pick up the dimension here and I specify the diameter. Make it 15. Now it is showing under constraint 2 DUFs.
Okay.
It's all very logical. Okay, you select the center and click here. Okay, like this. You specify the distance. Okay, make it 20. Now it is showing 1 DUF remaining. You again click here. Make it 25. Done. This is parametric modeling. Now you can click on, double click on any of these and change, and the circle will change. You can change the value and the circle will change.
What's written there?
Fully constrained. Or it is fully defined, you can say. 16. Right? This is 10, this is 25. Okay. Now let us say we make another circle. It's in the same sketch. So once again, your sketch has got 3 DUFs to be defined. But instead of defining the dimensions, now what we do is, we tell it to make the center points coincident. There should be coincident constraint. I think this is it. So, no. The interface has changed. Okay, this point should, no, this is not the one. Help me find, is it? No. Horizontal, vertical, no, this is parallel, this is perpendicular, this is tangency, equal in length. This is midway, okay. No. Not here. There's another way of doing it. If that constraint is not available, let's just delete this circle and draw another circle starting here. This is the constraint. So center point it has taken as that of the previous circle.
Yes.
Right? And only 1 degree of freedom needs to be defined. That is the size of this circle. You just click here and define it as maybe 8 mm. So we have 2 circles, one measuring 16 mm, the other one measuring 8 mm. Done. Now this sketch is fully constrained. So we tell it to close. I'm done with sketching. So this is what we have just created. 2 closed boundaries. We come to the task and we tell to pad it. So we give it a thickness of say 3 mm. Okay. Model में आपके पास ये pad बन गया. This is the body we have. In the body you have a pad, and in the pad you have the sketch. Sketch has been consumed by the pad. अगर आप thickness change करना चाहो, you can go back and tell it नहीं इसको 2.5 mm करना है. So the thickness changes. You can again go back to the pad parameters, make it 10. तो ये बड़ा हो जाएगा. ठीक है? इसको 2.5 कर देते हैं. You want to change the size? This you can click on the sketch make it 20, tell it to close, the model will change. Easy है ना?
Yes, sir.
हाँ. You see, this body contains pad and the pad contains the sketch. So just double click on the sketch, change the size, 2 मिलीमीटर कर दिया इसको, छोटा कर दिया सर्कल को, close, and the model will change. Followed?
Yes, sir.
Okay. Now let's term this body washer. इसमें rename होगा.
नीचे second last, sir.
Second last. This is rename. Let's call it washer. Now we just select this washer, right click and tell it to export, because the job of this software is done. Can you see the export option somewhere?
Export?
Export.
No, sir.
Here we have file export. Okay, first we have to select the washer, then click on file export. Okay, let's just call it a washer. This is exporting as STL file. Okay. Now we can close FreeCAD. This job is done. Let's not even save the file. Okay. Now we go to another software. This is the slicer. Let's first see where the STL file is lying.
We can search.
No, it's in FreeCAD files folder, this one. Here you have the washer. I'll just put it in different folder. I move to this one. Okay. Now I ask you to add part and I click on this washer.stl file that we had just exported from there, and it comes. You can select this. You want to print multiple copies, just click on this plus button.
How many copies to be?
जितनी कॉपीज आप करना चाहो, कम करनी है कम कर दीजिए, अप टू यू. हम नॉर्मली कम से कम 2 कर लिया करते हैं ताकि जब एक पे प्रिंटिंग होके जाए उसको थोड़ा ओके उसको थोड़ा ठंडा होने का टाइम मिल जाए. सो इट द हेड गोज टू द अदर वन. इतने में पहले वाली थोड़ी सेट हो जाएगी. ठीक है, तो कम से कम 2 प्रिंट, अगर छोटा पार्ट है तो 2 प्रिंट कर लेने चाहिए, बड़ा पार्ट है तो 1 भी हो जाएगा, बिकॉज इन बिटवीन उसको कूलिंग का टाइम चाहिए, नहीं तो अपसेट रहेगा वो. ठीक है, आप इनको पकड़ के कहीं पे प्लेस करना चाहो तो ऐसे भी कर सकते हो. ठीक है, ओरिएंटेशन चेंज करनी है, कुछ भी करना, दैट यू कैन डू. ठीक है, ये आपको देखना पड़ेगा कि पार्ट कौन सा कैसे प्रिंट करना है. मतलब इसको वॉशर को आप अगर खड़े करके प्रिंटिंग करोगे तो उसको मटेरियल को सपोर्ट नहीं मिलेगी. तो इसको हॉरिजॉन्टल रख के प्रिंट करना सही है ना. जैसे अभी जो आप पार्ट देख रहे हैं इसमें एक फ्लेंज है, तो फ्लेंज को ऊपर करोगे तो इसको नीचे से सपोर्ट बिल्ड करनी पड़ेगी, फालतू में टाइम जाएगा. तो इसको ऐसे प्रिंट कर लो. सो यू हैव टू डिसाइड ऑन द बेस्ट ओरिएंटेशन. वॉशर को सीधे उल्टे का फर्क नहीं पड़ेगा, बिकॉज इट्स सेम बोथ वेज. राइट, अब ये करने के बाद ऑल यू हैव टू डू इज जस्ट क्लिक ऑन दिस प्रीव्यू. देखो मैंने इसमें प्रिंटर के पैरामीटर्स ऑलरेडी सेट कर रखे हैं, कौन सा फिलामेंट है क्या है. जस्ट क्लिक ऑन प्रीव्यू और इसने इसकी लेयर्स, दीज आर द लेयर्स. ये पहली लेयर ऐसी होगी फिलामेंट की. ठीक है, सेकंड, थर्ड, फोर्थ, फिफ्थ, सिक्स्थ, सेवंथ. तो 7 लेयर्स में ये पूरी बन जाएगी 2.5 मिलीमीटर थिक. ठीक है, ये करने के बाद जस्ट क्लिक ऑन एक्सपोर्ट जी कोड. तो weather.g कोड, ये फाइल एक्सपोर्ट हो गई. तो ये प्रोग्राम बन
सर
गया.
ये कहाँ से किया दोबारा?
ये रहा एक्सपोर्ट जी कोड.
अच्छा,
ये माउस है वहाँ पे. So this is the slicer. पहले हमने free CAD यूज किया, now we are using slicer. क्यों यूज कर रहे हैं? Because ये free है, ठीक है. अब देखो washer.stl फाइल ये थी, तो washer.g कोड है. दिस इज बेसिकली टेक्स्ट फाइल. तो आप इसको चाहो यू कैन क्लिक ऑन ओपन विद नोटपैड, एडिट इन नोटपैड कर लो. तो ये आपका प्रोग्राम है. आप देखोगे इसमें ज़्यादा आपको समझ में नहीं आएगा, लेकिन वट यू कैन अंडरस्टैंड इज कि एक्स वाई जेड कोऑर्डिनेट्स ही मूव कर रहे हैं सारे में, ठीक है. और लास्ट में ई है, दिस इज एक्सट्रूडर. तो एक्सट्रूडर जितना फिलामेंट फीड कर रहा है, बिकॉज इट हैज़ बीन टोल्ड कि 0.4 mm की नोजल है और 1.75 mm का फिलामेंट है. तो कितना नीचे वॉल्यूम चाहिए और कितना ऊपर से फीड करना पड़ेगा, दैट नोज. कैलकुलेशन है सिंपल मैथमेटिकल. तो इसने ये सारी स्टेपर मोटर्स की कमांड के लिए ये कर दिया है ना. ये सारी मैथमेटिकल टेक्स्ट फॉर्म में वैल्यूज आ गई. कुछ एक होती हैं इसमें GM कोड होते हैं. वन इज द ज्योमेट्री कोड्स, जैसे अपने अभी एक्स वाई एक्सक्लूजन के देखें. जेड के भी होंगे, जब लेयर चेंज करेगा तो जेड की कमांड जाएगी, है ना, एक लेयर के बाद. एक इसमें होते हैं मशीन कोड्स. इसका फैन चलाना है, टेम्परेचर सेट करना है, वो मशीन कोड्स में आएगा. टेम्परेचर कितना सेट करना है बेड का, एक्सक्लूडर का. आप पहले इसको यहाँ से भी शुरू कर देते हैं. हम जितना हम लोड करेंगे तो कम से कम वो आपका टाइम बच जाएगा. सो बेड आई एम हीटिंग टू, और इसी में टाइम जाएगा. 58 डिग्री इसमें सेट कर दिया. ओके, तो बेड हीटिंग तो मैंने मैनुअली शुरू कर दी इसकी, राइट. तो अब what we have to do is we have to take out this card, we insert the card into the laptop, ओके. तो जो हमारा अभी प्रोग्राम हमने बनाया है, washer.g कोड, तो हम इसको SD कार्ड में कॉपी कर लेते हैं. सिंपल, यू डू इट डे इन एंड आउट.
ये एज नोटपैड में हमने कॉपी किया इसको?
ना SD कार्ड में कॉपी कर दिया. टेक्स्ट फाइल ही है ना.
नहीं वो तो बाद में करा
मैम. ये नोटपैड में तो खोल के देखा था इसको. नोटपैड में किया कुछ नहीं हमने इसको. कई बार एडिट करना पड़ जाता है प्रोग्राम.
ये आपका स्लाइसर में ही था.
स्लाइसर से एक्सपोर्ट कर दी ना टेक्स्ट फाइल.
अब करी ना,
जो आपको नोटपैड में खोल के दिखाई थी वो स्लाइसर ने राइट की थी.
हाँ.
FreeCAD had written an STL file which was a geometry information file.
Right.
तो उसको हमने रीड किया स्लाइसर में, एंड स्लाइसर मेड एन NC प्रोग्राम फाइल.
Right.
वो हमने नोटपैड में खोल के उसको देख लिया.
Okay.
ठीक है. तो आपका बेसिकली जो सॉलिड मॉडल था अब वो प्रोग्राम की फॉर्म में आ गया, विच प्रोग्राम इज कस्टमाइज्ड टू रन ऑन दिस प्रिंटर, बिकॉज इसके पैरामीटर स्लाइसर में डाले हुए हैं.
जो G कोड फाइल है ये हमारी कहाँ पड़ी थी?
ये पड़ी है. इसको मैंने अभी मेमोरी कार्ड में कॉपी कर दिया है.
ओके.
जस्ट वांटेड टू शो यू कि ये सिंपल टेक्स्ट फाइल है. तो टेक्स्ट फाइल है तो आप इसको एडिट भी कर सकते हो.
Right.
यू सी समटाइम्स व्हाट हैपेंस इज प्रिंटिंग चल रही है, देयर इज अ पावर फेलियर. आपका बहुत बड़ा पार्ट था, उसमें 10 घंटे में प्रिंट होना था, 6 घंटे हो चुके हैं, 7 या 8 घंटे हो चुके हैं, ठीक है ना. बीच में लाइट चली गई. यू हैव 2 ऑप्शंस. वन, उसको डिस्कार्ड कर दो, नए से शुरू करो, फिर लाइट जा सकती है. प्रिंटर माल फंक्शन कर सकता है, है ना. कुछ ना कुछ तो हो ही सकता है, बिकॉज जो पार्ट्स थोड़ी देर में प्रिंट होते हैं द चांसेस ऑफ सक्सेस आर मोर. जो पार्ट्स बहुत लंबे लीड टाइम वाले होते हैं 3 दिन में पार्ट प्रिंट होता है, तो अब 2 दिन का इसका जो काम है उसको डिस्कार्ड थोड़ी करोगे. देन व्हाट टू डू, फिर आप नॉर्मली उस पार्ट को हाइट नाप लेते हो कि यहाँ तक प्रिंट हुआ था इस डेट लेवल तक. उतना सारा प्रोग्राम उस डेट को इसमें सर्च करके आप उतना सारा प्रोग्राम की लाइंस उसमें से डिलीट कर दोगे मैनुअली. शुरू वाली रख लोगे, नोजल गर्म करनी, सारा वो शुरू वाली रख लोगे. बीच वाली सारी जो उसने घूमना फिरना था वो डिलीट करनी पड़ेगी, बिकॉज नहीं तो आपका हेड आके पार्ट में लग जाएगा बीच में, उसको उखाड़ देगा नीचे से, ठीक है ना. तो डिलीट करोगे, फिर क्या ऊपर जाके शुरू करेगा तो सब्सिक्वेंट लेयर से प्रिंटिंग शुरू कर देगा. दिस इज ऑल द एडिटिंग दैट यू हैव टू डू इन द प्रोग्राम फाइल एट टाइम्स. प्रिंटर माल फंक्शन या पावर फेलियर के केस में, राइट, दैट्स डन. तो हमने इसको अब SD कार्ड में कॉपी कर दिया. अब हम क्या करेंगे, रिमूव द SD कार्ड. अच्छा कर दिया मैंने, इसको यहाँ से निकाल लिया. और इसको यहाँ पे लगा दिया, शो मीडिया इंसर्टेड। अब आप लोग यहाँ आ जाओ, अगर इस पे देखना है आपने, लाइट ऑन करनी है, आपको ऊपर खड़े होके दिखेगा शायद इस पे। क्या करें, इसको घुमाइए, पीछे करें, दिख जाएगा। इसका सिंपल सा मेन्यू है, एक रोटरी से चलता है ये। आई क्लिक टू एंटर इनटू द मेन्यू, इन्फो स्क्रीन, मोशन, टेम्परेचर, कॉन्फ़िगरेशन। मुश्किल है देखने में, है ना।
तो इस टेबल को थोड़ा
एक काम करते हैं, इसको घुमा लेते हैं प्रिंटर को, थोड़ा फिर तो हाथ लगाइए। और घुमा लो, मैं भी ऊपर ही आ जाऊंगा। प्लग लगा दीजिए। माइक्रो कंट्रोलर है तो ये 2 सेकंड में बूट हो जाता है, अनलाइक योर पीसी। दिस इज पैरेलल, दिस इज अगेन फ्रीवेयर। प्रोजेक्टर बंद कर दें, ऑफ नहीं आ रहा है ना। somebody please switch off the projector, it's not required। आप ही कर दो। अभी देखो ये दिखा रहा है XYZ, बंद करके ऑन किया ना, तो इसको अपनी पोजीशंस नहीं पता। वैसे तो प्रोग्राम में भी ऑटोमेटिक पोजीशन डिटरमिन करने की है, बट इसमें देखो मैनुअली कैसे करोगे आप। मोशन पे जाओगे, आप मूव एक्सिस कर सकते हो। मूव एक्स अगर करोगे, हमने हाथ से भी हिला दिया था ना, इसको पता ही नहीं अपनी पोजीशन इसकी कहाँ पे है। देख रहा है एक्स एक्सिस हिलता है, तो एक स्टेपर मोटर को कमांड दे रहा है। यू कैन कम बैक, मूव वाई। ओपन लूप है, अगर आप ज़्यादा लेके जाओगे तो सिरे पे आके रुक के कट 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 करेगी।
ओके,
ठीक है, ओके। सिमिलरली मूव जेड, ऊपर उठा। अब इसको अभी भी अपनी कोऑर्डिनेट नहीं पता, इंक्रीमेंट तो हम कर रहे हैं, तो आप इसको ऑटो होम कर सकते हो। ऑटो होम में क्या करेगा, इसमें ना 3 लिमिट स्विचेस लगी हुई हैं, उनको सेंस करते हुए आगे बढ़ेगा। एक लिमिट स्विच यहाँ पे है, मैं इसको दबाता हूँ ना तो ये ऑन होती है। एक यहाँ भी आपको दिख जाएगी आराम से, ये देखो, ठीक है। तो हम इसको बोलते हैं ऑटो होम, वहाँ से अपनी पोजीशन सेंस करता है। लिमिट पे जाके रुक गया, ये भी लिमिट पे जाके रुक गया। अब जेड वाला लिमिट पे जाके रुकेगा। तो 0 0 0 कोऑर्डिनेट्स हो गए इसके, उस कोऑर्डिनेट पे। ओके, डन। अब देखो इन्फो सिग्नल 0 0 0 दिखा रहा है। अब आप मूव करोगे तो आपको कोऑर्डिनेट दिखाएगा कि कितने पे पहुंच गए। तो हम क्या करते हैं, हम टेम्परेचर मैनुअली सेट करते हैं पहले। वैसे तो प्रोग्राम में भी होगा, बट हम टाइम सेव करेंगे, इससे पहले कर देते हैं। बेड 60 के आसपास हमें रखना। ओके, नोजल 184 कर दिया। नोजल के नीचे कूलिंग फैन लगा हुआ है, इसको ऑन कर देते हैं स्पीड पे, ठीक है, ताकि ओवरहीट ना हो। नहीं फिर ऊपर से फिलामेंट मेल्ट होना शुरू हो जाएगा, वहाँ पे हार्ड चाहिए। नहीं तो रोलर उसको फीड कैसे करेगा अगर ऊपर ही मेल्ट हो गया। बिल्कुल बॉटम पे जाके ही फिलामेंट ने गर्म होना है, वो इसकी मेल्टिंग की जोन है। ओके, ये आपको दिखा रहा है नोजल का टेम्परेचर, ये दिखा रहा है बेड का टेम्परेचर। बेड इज अराउंड 100 वाट्स, हीटर इसमें सारे में लगा हुआ है नीचे। ये सिलिकॉन के पैड्स हैं, इसके ऊपर ग्लास स्लैब पे आ रहा है। और ये आपका फिलामेंट का 40 वाट का हीटर है, छोटा सा, मतलब छोटा जल्दी गर्म होता है। ठीक है, इन द मीन टाइम हम इसके साथ थोड़ा सा खेल करते हैं। मूव एक्सिस एक्स एट ए टाइम 10 mm, 1 mm या 0.1 mm। ठीक है, 0.1 करोगे तो थोड़ा थोड़ा हिलेगा। करके देखो। ठीक है, अब इसको 1 mm पे लेके जाओ, प्रेस इट वंस, 1 mm पे ले आओ। अब ठीक है, अब 10 पे ले आओ। 0 से आगे नहीं जाएगा, उसको पता है ना 0 से पीछे जाएगा ही नहीं। स्टेपर मोटर है, ओपन लूप है, अगर आप इसको पकड़ के कहीं छोड़ दोगे, इसको नहीं पता चलेगा कि मेरी पोजीशन हिला दी है। तो सारी ज़्यादातर CNC मशीन ओपन लूप ही चलती हैं, वो एक बार अपनी पोजीशन सेंस करते हैं। घर पे प्रिंटर पड़ा इंकजेट या डॉट मैट्रिक्स, जब ऑन करते हो पहले क्या करता है,
चलता है,
हेड एक साइड पे जाता है, फिर वहां से वापस आता है, वो बेसिकली लिमिट स्विच पे जाके हिट करता है। फ्रॉम देयर इट रिकवर्स इट्स पोजीशन। आंख पे पट्टी बांध के चलो कि इसको पकड़ लिया मैंने, 10 कदम ऐसे जाना है,
रेफरेंस लेता है वहां से,
रेफरेंस वहां से लेगा। ठीक है, ये बेसिकली सारी मशीन डफर होती हैं। ठीक है, जो AI बेस्ड है वो क्या करेगी, कैमरा से पोजीशन सेंस करेगी, वो दूसरी चीज है। तो ये सिर्फ ओपन लूप सिस्टम है, इसने वहां जाना, वहां से रेकन करेगा, इतने स्टेप्स इधर को, इतने स्टेप्स उधर को, इतने उधर को,
बीच में नहीं पता होता है कहाँ है,
इसको कुछ नहीं पता, ये अंधा है प्राइमरीली। ठीक है, ओके, अब हमारा टेम्परेचर लगभग अचीव हो गया, तो हम क्या करते हैं इसमें प्रिंट फ्रॉम मीडिया, ये मीडिया ना, ये हमने वॉशर जी कोड प्रोग्राम इसमें किया था। स्टार्ट प्रिंट वॉशर जी कोड, यस राइट। तो प्रोग्राम के शुरू में एक वो स्लाइसर ने डाला हुआ कि 0 सेट करना है, वो 0 फिर से करेगा ये, बिकॉज प्रोग्राम में इंस्ट्रक्शन है उसकी। ठीक है, फिर ये वेट करेगा कि टेम्परेचर अचीव हो जाए। 203 पे सेट है, 192 है।
वहाँ पे हमने टेम्परेचर और वो कैसे किया था,
वो उसमें पहले से डिफाइंड है ना स्लाइसर में।
प्रिंटर स्लाइसर में
हाँ, स्लाइसर में प्रिंट सेटिंग, फिलामेंट सेटिंग्स, ये सारी करनी पड़ती है, बिकॉज एवरी फिलामेंट हैज गॉट इट्स ओन सेटिंग्स
एंड प्रॉपर्टीज
उसके हिसाब से पैरामीटर्स डालने पड़ते हैं। हम क्या करते हैं, उस फिलामेंट की सेटिंग की फाइल सेव कर लेते हैं। व्हाटएवर फिलामेंट यू लोड, अगर 10 तरह के फिलामेंट्स पड़े हैं आपके पास, तो जो फिलामेंट डालोगे उसकी फाइल आप इंपोर्ट कर लो।
ओके, ये आपका पॉलीयूरेथेन के हिसाब से।
हाँ जी, हाँ जी, पॉलीयूरेथेन के भी मल्टीपल है, ये ब्लैक वाला एक वाइट है, उसके पैरामीटर्स डिफरेंट है।
अच्छा,
तो फॉर एवरी फिलामेंट यू हैव टू फाइन ट्यून द पैरामीटर्स। अब मैंने बताया ना, मेरा तो मैंने लैपटॉप रीबूट ही किया, सारा रिफॉर्मेट किया, तो मेरी पैरामीटर्स फाइल यूज हो गई है, फिर से करनी पड़ेगी। छोटा पार्ट है ना, बड़े पार्ट में तो ये देखो इतनी ही प्रोग्रेस इंडिकेटर है, 1/3 के करीब हो गया अभी। ID 8 mm, OD 16 mm।
अच्छा, वो लेयर बाय लेयर वर्क कर
लेयर बाय लेयर, ये Z की हाइट दिखाएगा आपको 1.05 mm, 0.3 के हिसाब से बढ़ रहा है, पहले 0.25 की है, फिर 0.33। ये बीच बीच में कभी बेड को गर्म करता है, कभी फिलामेंट को ना, ये टेम्परेचर जब ये वाइट है तो ये ऑन है।
जो ये सारी इलेक्ट्रॉनिक वायरिंग है, दिस ऑल पार्ट्स तो आगे दिस वायरिंग इज
मैनुअली और डन एट होम ड्यूरिंग लॉकडाउन। दिख नहीं रहा है, कोई बॉटल तो वो है नहीं कि कहीं से आपने रेडीमेड लिया, सब जुगाड़ है।
अच्छा जुगाड़ है सर,
इट टीचेस यू एक्चुअली, जुगाड़ टीचेस यू अ लॉट। आप अगर बहुत क्लोजली लाइट डाल के देखो, हम नोजल से कूल आउट होता दिखेगा मटेरियल। तो ना आगे इसकी स्टेपर मोटर्स के भी स्टेप्स दिखेंगे। इधर आपको ना फिलामेंट फीडिंग का भी दिखेगा, ये गियर आपको दिखेगा मूवमेंट, जब भी छोड़ के आगे जाएगा तो पीछे को मोड़ता है इसको, ये यहाँ पे गियर आप देख सकते हैं।
ये पहले एक को क्यों नहीं कंप्लीट कर रहा?
हैं?
बेटा लेयर
एक लेयर उसने पूरी करनी है, नहीं तो जब मूव करेगा उसको अगर प्रिंट पहले कर दी तो उसमें जाके हिट कर देगा। तो Z ने सिर्फ ऊपर को ही जाना होता है। देखो X और Y की कोऑर्डिनेशन कैसे सर्कल ड्रॉ करने के लिए, एक ऐसे हिल रहा है, एक ऐसे, साइन और कोसाइन वेव्स हैं बेसिकली। चीज़ दिखाऊँ, इस पे ना मैंने पंजाबी के फॉन्ट्स किए थे प्रिंट, पंजाबी यूनिवर्सिटी पटियाला इस पे लिखा होगा, साइड से लाइट डालोगे तो दिखेगा। यूनिकोड पंजाबी फॉन्ट्स में प्रिंटिंग की हुई है इस पे। इट्स बेसिकली मोबाइल होल्डर। हाँ हाँ, ये देखो अपना मोबाइल, ये ब्लैक पे अच्छा दिखता है मोबाइल देना, इस काम के लिए है ये सब मोबाइल होल्डर।
वेरी नाइस होल्डर।
आपको पसंद है, आप ले जाओगे इसको तो और प्रिंट हो जाएगा।
हम तो ये सोच रहे सर, जो ना बताते पता भी नहीं चलता है मोबाइल होल्डर में।
हाँ
नहीं, ये बंद हो जाता है एक्चुअली, इसमें ना पूरा करोगे तो क्लिक हो एक बंद हो जाएगा, ये फोल्ड हो जाएगा आपकी पर्स में रहने के लिए ना।
अच्छा, ये ऐसे बंद हो
हाँ
जाता
हाँ हाँ हाँ, हो रहा है कि नहीं? ये एक्सपेरिमेंटल सा पार्ट है। हो गया? हो गया। You can keep it as a small gift from this program.
3D प्रिंटिंग लाइव एग्जांपल।
हाँ। ये देखो छोटे छोटे इस टाइमिंग बेल्ट की पुलीज जो नहीं मिलती मार्केट में, यू कैन प्रिंट। ये जो इसमें बेल्ट यूज करते हैं, टीथ होते हैं इसमें, तो इसी के साइज की है ये पुली।
ओके।
अभी ठंडा होने की वेट कर ली इसने, अब ये आपको दे दिया।
ओके,
फिनिश्ड। अब आप इसको उखाड़ सकते हैं ऊपर से। जो आपका वो नीचे ये है, बस दिस इज ओनली वेस्टेज।
ये उसने एक बार बॉर्डर मार्क किया।
वो एक्चुअली कई बार होता है जब ये पहले गर्म होते हैं ना, तो थोड़ा सा फिलामेंट ऊज आउट होके नीचे ऊपर खाली कैविटी बन जाती है। नहीं, शुरू में मिस ना करे इसलिए बॉर्डर बनाता है, जस्ट टू इंश्योर कि वो अब आ गया फिलामेंट। यू कैन कीप दिस,
वेरी फाइनली फैब्रिक।
बच्चों को दिखाने के लिए कि हाँ हमने ये किया। टीपीयू थोड़ा सा महंगा है। दिस रोल इज 1 kg रोल कॉस्ट अराउंड आई थिंक 2500 रुपए का। पीएलए का सस्ता होता है, वो 1000-1500 का मिलता है। उससे सस्ते भी आते हैं, लेकिन फिर वो कई बार ना फिलामेंट्स परेशान करने वाले होते हैं, होमोजेनिटी नहीं होती। रख लो बेटा, ये रख लो, ये रख लो, जो जो आपको अगर क्लास में जाके कहीं दिखाना है। बट यू आर पीएचडी स्टूडेंट्स ना, तो घर पे जाके दिखाओगे। Should you switch it off?
Yes, sir.
ये देखो बेड गरम, 60 के आसपास होगा ना, ऊपर तक इतना नहीं है, 50-55 होगा ऊपर। तो इसमें थर्मोकपल सेंसर लगा हुआ है। इधर भी एक वाइट वाली तारें हैं ना, ये थर्मोकपल की है इधर।
ओके।
एक इसमें है, एक इसका अंदर पीछे लगा होता है सेंटर में बेड के नीचे, तो वो दोनों की रीडिंग ऊपर आती है इसमें।
Very nice demonstration, sir.
Thank you. Good that you all
Truly
enjoyed.
new knowledge. बच्चों की तो भी बहुत लर्निंग एज है।
ये बच्चे तो बहुत आगे जाएंगे आज की डेट में, तो मल्टी फिलामेंट, मल्टी मटेरियल है ना। फिर देन यू हैव
सम ऑफ यू आर वर्किंग ऑन मेटल फ्रेमवर्क्स पे, कोई हेल्प बोल रहा था। कौन काम कर रहा है? आप कर रहे हैं?
हाँ जी।
ओके।
हाँ जी सर।
केयरफुल सर।
नहीं, कुछ नहीं है। बिना वजह के सिर्फ एक ही स्पीशी हर्ट करती है, दैट इज होमोसेपियंस।
अच्छा, ठीक है जी।
I'll need somebody's help to put it in the car.
Yes sir.
I hope you enjoyed.
Yes, sir.
A lot.
अब बस ये है कि करो कुछ ना कुछ,
एक्सप्लोर।
हाँ एक्सप्लोर करो, सब इंटरनेट पे अवेलेबल है। एक ना जैसे आप विकिपीडिया देखते हो फॉर लुकिंग एट द आर्टिकल्स या नॉलेज के लिए, है ना, देयर इज अनदर प्लेटफॉर्म दैट इज गिटहब, कभी देखा है? गिटहब पे लोग
पुराना ही गेम चल रहा है एक बारी गल कर
Some want to attend online.
every we are changing the link
Okay.
every session so that nobody
हाँ नहीं मैं वैसे पूछ रही थी कल ऑनलाइन अगर है तो जैसे मेरी स्टूडेंट की प्रॉब्लम थी उसको आ नहीं पाई तो मैं इसलिए आप पूछ रही थी कि अगर ऑनलाइन है पॉसिबल तो उसको बोलते
YouTube पे चलाने की जरूरत
तो ये हर सेशन वाइज फिर लिंक्स लेने पड़ेंगे ऑनलाइन सीधा ज्ञान कोर्स अगर मैं अभी डालूँ तो आ जाएगा जैसे यहाँ यादवंद्रा कॉलोनी में स्टे है ना मेरा तो मुझे वहाँ से गूगल मैप लगाया था मैंने तो आज पता नहीं कौन से रास्ते से लेके आया वो पीछे वाला बैक गेट से उसने एंट्री दी आई वॉज नॉट अवेयर ऑफ एक वो गेट पास का सर मेरे को कल तो किसी ने रोका नहीं गेट पे मुझे बनवाना है कि जस्ट अ मेल वॉज इनफ आपकी तरफ से एक मेल आया था मुझे
मेल भेजा मैम तो वो जैसे आपको गेट पे रोकेंगे ना तो उनको कह दो कि मेरा गेट पर
ओके मतलब फिर बना होगा आई नीड टू कलेक्ट
You wait for the students?
या बेटा बच्चों को बुला लो बाकी को
वो जो आपको लिंक भेजा आज के ना वो
इनसे बात करो
वो तो क्या
आज का कोई लिंक कहाँ है
अभी नहीं है मैंने इस पे नहीं है सर को भेजा
Better, it's fine.
एक बार
जी सर
ये हाँ
देखो
ये इसको देखो
ये आदमी भेज दो सर
इसको करना
मुझे
पिछों भी करके फिर ओके ओके
They're saying this cable is disturbing them. So can we do one thing? You can remove it here and then bring from your bag. Should I help you?
Yeah. It's easier. Just get this one.
It's okay, it's okay. Bas. Now I'll paste it here.
Yeah.
Saying this cable is disturbing them. So can we do one thing? You can remove it here and then bring from your bag. Forward.
पॉसिबिलिटी है कि जेड़ा पर मैडम ने वाइट शरक पाया है वायर ਦੇ ਨੀਚੇ ਲੈ ਲਈ ਹੈ ਵਾਈਟ ਸ਼ਰਕ ਪਿੱਛੇ ਜਦੋਂ ਆ ਰਹੀ ਹੈ ਵਾਇਰ ਜਦੋਂ ਪਿੱਛੇ ਹੀ ਆ ਰਹੀ ਹੈ ਹਾਂਜੀ ਇਹ ਸ਼ਰਕ ਨੂੰ ਵੀ ਵਿੱਚ ਕਲਿੱਪ ਕਰ ਦਿਓ
ਓਕੇ
ਤਾਂ ਕਿ ਸ਼ਰਕ ਜਦੋਂ ਨਾਲ ਟੱਚ ਹੁੰਦਾ ਹੈ ਨਾ ਇੱਕ ਉਹ ਵੀ ਡਿਸਟਰਬੈਂਸ ਕ੍ਰੀਏਟ ਕਰਦਾ ਹੈ ਮਾਈਕ ਦਾ ਬਸ ਫੇਸ ਅਪ ਕਰ ਦੇਣਾ ਨਾ
ਬਸ
ਸ਼ਰਗ ਔਰ ਹਾਂਜੀ ਟੌਪ ਨੂੰ ਦੋਨਾਂ ਨੂੰ ਕਲਿੱਕ ਕਰ ਦਿਓ ਮੈਮ ਮਾਈਕ ਅੰਦਰ ਚਲਾ ਗਿਆ ਮਾਈਕ ਬਾਹਰ ਆਣਾ ਚਾਹੀਦਾ ਹੈ
ਮਾਈਕ
हाँ,
ਫਿਰ
हाँ,
ਇਦਾਂ ਆਊਗਾ it has to come yeah
Otherwise, just the fabric will make noise.
ਬੇਸ਼ੱਕ ਇਸ ਸਾਈਡ ਤੇ ਕਰ ਦਿਓ ਕੋਈ ਇਸ਼ੂ ਨਹੀਂ ਹੈ ਇਸ ਗੱਲ ਦਾ ਬਟ ਹਾਂ ਵਾਇਰ ਜਿਹੜੀ ਹੈ ਇਹ ਸਾਨੂੰ ਇਸ ਬੈਕ ਤੋਂ ਲੈ ਲਓ ਜਿਵੇਂ ਤੁਸੀਂ ਵਾਇਰ ਇੱਥੋਂ ਲੈ ਕੇ
ਫਿਰ
ਆਏ
ਇਦਾਂ ਨਾ ਇੱਧਰ ਆਏ
ਨਹੀਂ ਆਏਗਾ ਇੱਥੇ
ਸਮਝ ਗਈ
ਤੁਸੀਂ ਸਾਈਡ ਬੇਸ਼ੱਕ ਇਹੀ ਰੱਖ ਲਓ ਬਸ ਅਸੀਂ ਇਹ ਕਹਿੰਦੇ ਕਿ ਜਿਹੜੀ ਵਾਈਟ ਬਲੈਕ ਵਾਇਰ ਹੈ ਨਾ ਇਹ ਮੈਡਮ ਦੇ ਸ਼ਰਗ ਦੇ ਅੰਦਰੋਂ ਲੈ ਲਓ
ਓਕੇ ਗਾਟ ਇਟ ਪਰੇ ਆਉਣੀ ਬਾਹਰੋਂ ਹੀ ਹੈ it will not come
ਤਾਂ ਇਹ ਜਿਹੜਾ ਟਰਾਂਸਮਿਟਰ ਹੈ ਨਾ ਮੈਮ ਦੇ ਇੱਥੇ ਹੈ ਨਾ ਸਰ ਕਹਿ ਰਹੀ ਸੀ ਇਹ ਬੈਕ ਤੇ ਜਿਹੜਾ ਹੈ ਨਾ ਨੈਕ ਲਾਈਨ ਏਰੀਆ ਬੈਕ ਤੇ ਜਿਹੜੀ
ਟਰਾਂਸਮਿਟਰ
ਹਾਂ ਟਰਾਂਸਮਿਟਰ ਪਿੱਛੇ ਡੱਕ ਕਰ ਦਿਓ ਸ਼ਰਗ ਦੇ ਪਿੱਛੇ ਟਰਾਂਸਮਿਟਰ ਸਾਨੂੰ ਦਿਖਣਾ ਹੀ ਨਹੀਂ ਚਾਹੀਦਾ
ਓਕੇ
ਟਰਾਂਸਮਿਟਰ ਤੇ ਸਾਨੂੰ ਹਿਡਨ ਨਹੀਂ ਆ
okay I'll tuck it at your back where to tuck it will be
Maybe here?
wait I'll do it don't I'll take it from inside don't worry no worry
ਆਪ ਜੀ ਦੇਖੋ ਤੁਹਾਨੂੰ ਆਡੀਓ ਮਿਲ ਰਹੀ ਹੈ ਕਿਉਂਕਿ ਮਾਈਕ ਜਿਹੜਾ ਹੈ ਉਹ ਵੀ ਔਨ ਕਰਤਾ ਸੀ ਮੈਂ
wait now I need to
ਦੇਖੋ ਚਾਰਜ ਕਰਤੇ ਪੂਰੇ ਜਿਸ ਟਾਈਮ ਬਾਈ ਚਾਂਸ ਸੈੱਲ ਹੋ ਗਿਆ ਨੀਡ ਪਏਗੀ ਆਪਾਂ
now it's perfect I'll tuck it along with your shrug it will not move fine
Better?
Thank you.
Is this better? No? No interferences?
better
you should say perfect now
Are you now happy or we need to do something else?
This is fine actually. Yeah.
So,
और आना है बच्चों में भी बेटा it's 2:30
shall we just start?
Yes, ma'am. We can start.
Because I'm not, yeah, so because if they're not coming. Okay, let's. It's probably easier to see this slides if the lights are off.
ਕੋਈ ਕਾਰਡ ਚਲਾ ਰਿਹਾ ਨਾ ਕੋਈ ਕਾਰਡ ਤੋਂ ਆਪਾਂ ਦੇ ਕੋਈ ਕਾਰਡ ਚਲਾ
are you feeling the weight at the back
No, that's okay. That's okay. I was just wondering if the slides are easy to see with a light, so maybe we need a bit less light.
You want to switch off?
Yeah.
Okay.
Yeah, that makes the screen easier to see. Okay, thank you for coming. This afternoon, during this lecture, we'll be talking about capillary electrophoresis. So after a great morning talking about 3D printing, we're now changing gears and we're moving into analytical chemistry. So we will be revisiting 3D printing next week. So don't forget everything that you've seen this morning, but we had some timetabling challenges moving different modules around. So where we talked about field portable analytical instrumentation yesterday, today we'll be delving in a lot more detail in one of the separation techniques that we talked about, and that's capillary electrophoresis. In capillary electrophoresis, we separate molecules based on their size to charge ratio. You may have done some gel electrophoresis. All electrophoretic techniques are part of the same family, and they are all based on the migration and separation of charged particles, typically ions, but it could also be cells or bacteria, under the influence of an electric field. To apply this electric field, we need to have in electrodes, the positive electrode, or called the anode, and a negative electrode called the cathode. And these two electrodes are applying a potential difference across an electrolyte. And if we then have a sample sitting in there, this sample can be separated based on the differences in electrophoretic mobility. As I already referred to, there is a very large family of different electrophoretic techniques. Already in the 19th century, Karl Rausch discovered that there's a relationship between the ionic conductivity and the speed at which ions move in an electric field. And therefore the migration order is determined. Tiselius then found out that if you have a discontinuous electrolyte system, it can have something that he initially termed moving boundary electrophoresis, and that's later been termed isotechophoresis. That's something that we put on hold at the moment, because tomorrow you will have Professor Baga coming from IIT Delhi, and he will be talking a lot about isotechophoresis, the way that it works, and the way that you can use computer simulations to predict how the separation is going to look like before you apply it in the laboratory. So he will be going through computer simulations of isotechophoretic systems. In 1939, zone electrophoresis, where analytes move in their zone, was established, and that's what we'll be spending most of today about, understanding how zone electrophoresis works. Gel electrophoresis is the separation based on the size and the difficulty of large molecules, like proteins, moving through a gel, and there's agarose gel, starch, cellulose acetate, and later the acrylamide gels that have gained great popularity for DNA separations. Electrochromatography is a hyphenation between electrophoresis and chromatography. So you still use an electric field to move your target analytes from one electrode to the other, but there will be an additional interaction with the stationary phase, like is happening in chromatography. And we are in great hands. Professor Malik himself will be talking about chromatography and high-performance liquid chromatography later in this lecture series, to get you a better understanding of how the interactions of an analyte with a stationary phase work and how that can facilitate the separation. Isoelectric focusing, if you've got a background in biology, that's an important electrophoretic approach where you can separate different proteins based on their isoelectric points. Proteins are very large molecules, which means that they've got different acidic and basic groups, and they all have pHs where they're basic, so they're positively charged, they are acidic, so they're negatively charged, and there are points where they are neutral. And the pH where protein is neutral is unique for that protein, and that's called the pI, and that's the concept of isoelectric focusing. It puts all the proteins together in the band where they do not have mobility. Capillary electrophoresis was originally started in the early 80s, where Jorgensen found out that if you use a fused silica capillary where you've got a narrow bore of 50 micron, as we already learned yesterday, a narrow bore tube filled with a background electrolyte, the glass tube can actually significantly aid in the dissipation of heat, which means that you can do a high performance separation when using a very narrow column of water to do your buffer to do your separation in. Finally, we've already seen Professor Mans's name before. In 1992, Professor Mans demonstrated that in addition to infused silica capillaries, you can also do capillary electrophoresis in microchannels. So in capillary electrophoresis, the key to getting a separation is the speed at which the ions of different composition move in an electric field. And that is based on the charge to size ratio. So we can have here, we've got a molecule that is really large, but only it's got one positive charge, so its speed is relatively low. If this molecule gets slightly smaller, the speed goes up. If it even goes smaller, it gets even faster. So we have the mobility of an ion increasing with its charge to size ratio. And that means that ionization state is very important for determining the mobility of an ion. Because it's all predictable, we can make plots of the mobility of an ion, so the speed with which it develops in an electric field. So here we've got the negative electrophoretic mobility. Don't worry about the units at the moment. It is to get an idea what happens. But here we have, with the slower mobilities, we've got the organic ions. They are typically your low conductivity buffers. We can see HEBAs here, HEBA. So they are buffers that are large organic molecules. They have only typically, or most of these have only one anionic charge. Therefore, they have not a lot of charge relative to their size, and they've got a low mobility. Even though the smaller they get, or the more charged, here citrate and oxalate both can have double charges, they get faster. And then we've got in here the monovalent anions, where we have our relatively slow are our large ions, our phosphates. Then we go to our monovalent ions, and very quick here are our chlorides, bromides, cyanides. They are very small anions, and therefore we've got a very high charge to size ratio, which means that they're whizzing through the capillary if they are exposed to an electric field. Even faster if we go for monovalent ions. So we've got the divalent ions, like your hydrogen phosphates, sulfates. You can see again, the smaller they get with a divalent charge, the faster they go. Same for the trivalent and the tetravalent ions. So we have the size of the ion and the charge of the ion that both play a role in mobility. And for these small ions, you can see if we increase from monovalent to divalent, trivalent, tetravalent, we have a higher and higher mobility, which means that our ions move faster and faster. We can use these plots of mobility to predict what a separation looks like, or if we know what our ions are, understand what the order of electromigration would be. So here we've got a separation of a couple of different anions. We've got an electropherogram. So an electropherogram is the plot of the detector signal versus time, like you call a chromatogram when you do HPLC. So here we've got time on the x-axis, and we've got the signal intensity on the y-axis. If we look here at the first ion, do you think the one that comes first past the detector, is that a slow or a fast ion? Fast. So indeed, we look here at the fast ion, and our bromide is the first one that comes past the detector. Then we look at our nitrate, that sits a little bit slower than bromide. Cyanide sits even a little bit lower again, and you can derive back the other ions here that they will have a lower mobility down the line here of the monovalent ions. So by having a plot of the mobility of your ions, and when they're fully ionized, you can predict what their migration order is going to be. And it is very useful if you want to resolve some analytes, because maybe you can play with their apparent mobility using the pH. So these plots, even though they were made in the 80s, are actually still very useful if you're developing a capillary electrophoresis method. I already highlighted it before. For DNA-based separations, we had important events. We could do DNA gel separations in about 75. Then there was capillary electrophoresis, and then we had months moving that up to electrophoresis on a chip. And here we can see what an effect that is in the data that you actually realize in the laboratory. In the 70s, electrophoresis was done on a gel. And if you've done any biochemistry laboratory, you probably have run gel electrophoresis yourself. So make the gel, cast it, have a little comb to make the slots to pipette your sample in, apply the potential difference, and then use a dye to stain your bands. In this case, it's a DNA leather. And you can see where the different ions, or where the different DNA fragments have moved to. So we get the small fragments moving faster, so further along the gel than the lower one. Doing the same thing in a capillary. You can see that you can get very narrow peaks of your different base pairs. Again, here we've got the time and the signal intensity. We've got the small base pairs coming past the detector really early, and we've got the larger base pairs coming later. When Professor Mans had the idea of doing lab on a chip, there was a company founded, and he filed a patent, and then there was a company, and that got taken over by Agilent. And Agilent launched the HPLC chip. And here, this is an example of one of the HPLC chips. It's a device where you can load 9 different DNA samples, fill a channel network with the gel. There's a fluorescence detector integrated in the instrument. And you can get, just like we got with the capillary system, we get the small fragments going fast through the gel, and therefore getting a early detection, and the larger the fragments, the higher you go. I now would like...
Which company had this?
Agilent.
Agilent.
I now would like to draw your attention, and the screen doesn't have the resolution to properly see this.
Yeah.
So the time here is in minutes, the time here is in seconds.
Okay.
So by going down to the microscale, it is actually your separation becomes a lot faster. So same separation. Advantage of this device is that you can inject a number of different samples one after another, but you gain a lot in speed by miniaturizing the separation down to the microchip format. How come so? Why is capillary electrophoresis so much more efficient than when we were looking in the gel? And here we've got the picture of the gel. This is the capillary compared to an HPLC column. And then in the chip, the microchannel is even smaller. One of the reasons that electrophoretic separations are so efficient is because of the flow profile when you're pumping a liquid through a tube. In normal fluidic systems, in a garden hose, we get a parabolic flow profile. That's because if you think about a garden hose, the velocity at the walls of the garden hose will be 0. And the highest speed will be achieved in the middle because their flow there is not interrupted in any way by the effect of that the wall isn't moving. So if we've got the highest speed in the middle and the lowest speed at the edges, we get the so-called parabolic flow profile. And here you can see a separation where they apply the hydrodynamic pressure. And you can see that over time, the center moves a lot faster than the edges. And you can see that something that started off as perfectly separated zones following electrophoretic separation, by moving across to a hydrodynamic system, you actually destroy your separation by having this parabolic flow profile. This means that for chromatographic separation, you need to have much better resolution than for an electrophoretic one, because you need to accommodate for the fact that all your peaks aren't actually straight lines, they're all curves, which is just an effect of the hydrodynamics. In only electrophoretic systems, yeah?
Please repeat this one. Please repeat.
Repeat the flow profile?
Yeah.
So in HPLC, we've got a parabolic flow profile, which means that our zones physically need to be further separated than in electrophoretic separations, because otherwise they'll overlap. So if we look at the pictures here, this is at the end of an electrophoretic separation so that we've got the same starting point. We then apply a hydrodynamic flow. We just pump with pressure, which means that the middle is going faster than the sides. If you would have a single point detector, here after 33 seconds you would still just see the separated zones. Whereas if you would be looking here, you can't tell them apart anymore because they have merged together. Because for both of them, the center of the peak is so far ahead from the end of the peak that the center of the back zone has overtaken the back end of the first zone. That means that if you are developing a chromatographic separation, your peaks need to be physically further apart for your detector to be able to pick up the difference from one analyte to another. If we do electrophoretic separations, we've got a phenomena that is called the electroosmotic flow, and we have pictures about the physics of it a little bit later. But that is a flow that is created by the surface charge on the inner wall. So the flow, the pump is the walls. So the liquid at the wall is moving and it is dragging the liquid that sits in the bulk, that sits in the middle, along. Because there's so much wall and so little bulk, because we've got a high surface to volume ratio in a narrow bore capillary, it means that our flow profile is near flat. If you look really, really carefully, you can see it dipping in a little bit, but the flow profile is much, much closer to flat as it is when you're using hydrodynamic pressure. That means that you can have, in a very short space, you can still have very well resolved peaks. And that is the power of capillary electrophoresis. We can separate analytes in discrete zones on a very small footprint. To look a little bit deeper where that pump comes from, that pump is called the electroosmotic flow, or EOF. And if we think about the capillary wall, this is a fused silica capillary, or technically glass, which means that there are silanol groups on the sides, which means that the surface is, at most pHs, slightly deprotonated, which means the surface has a negative overall surface charge left. The silanol group on the surface has got a pKa. If you're at a pH below this pKa, the silanol groups will be deprotonated, and you're left with a negative surface charge all around the capillary, because this is a circular system. We have a fixed layer of cations that binds to that anionic surface, and they're not going to move anywhere. But very close to that fixed layer, we've got a diffuse layer of ions, where we've got counter ions and their counter ions that are attracted by that negative surface charge. If we apply a potential difference, there will be a dominance here of our cation ions. You can see that we've got more green here than red, which means that we get a force if we apply a negative potential on the right hand side. All these positive ions here with their hydrated shells will start pulling all the liquid across the wall of the capillary. So we've got a small ion, but every ion is hydrated, and it actually wears a fairly big water coat around it. And all the cations here, when they are exposed to an electric field, they want to move towards that negative electrode. And they drag the bulk liquid along, and that way they move liquid from one side of the capillary to another. If you do a capillary electrophoresis separation, you can actually see it. If you've got your separation running for a couple of minutes, and you start with your buffer reservoirs at the same level, it is a pump. So your levels in your reservoirs change because you're pumping liquid from one side to another, using the mobility of the cations in this diffuse layer near the surface. Some people like playing tricks. So if we put a cationic coating permanently on the wall, we can actually get the whole system to move in the other direction. So it is a function of the charge at the surface, the fact that we then get the fixed layer ions, the cations, they're not going to go anywhere, but we have an over-representation of the counter ions sitting here, so negative surface here. We've got an excess of positive ions in the diffuse layer, and they will be dragging the flow along. And that's the phenomena based that's driving the electroosmotic flow. It also means that your electroosmotic flow is dependent on your double layer thickness and therefore on your ionic strength, as well as on the pH, because the level of deprotonation of your capillary wall plays a role as well. So we have a lot of variables, but it is important to understand the processes that are all at play. Here we've got a graph of the electrophoretic mobility as a function of pH to demonstrate that. So we know that if we are at very low pH, most of our silanols will actually be protonated. So we've got a very low amount of charge, which means that we've got a very low electroosmotic flow. If our pH goes up, we can see that we get more and more of our silanol groups being deprotonated, which means that we've got an increasing density of negative charge on the surface wall, which means that we'll have more and more of these mobile cations that are going to be driving the flow. And with that, we can see that we've got an increase in electrophoretic mobility. So we've got a stronger engine. The higher that our pH goes, the stronger that our engine becomes, up to the point that all our silanides are fully ionized. And then it doesn't matter anymore if we further increase the pH, because that we've got nothing left to deprotonate. So it is important to understand it's a acid-base equilibrium. So we've got the faster changes in our electrophoretic mobility between pH 5.5 and about 8.5. And at lower pH and higher pH, it doesn't change as much. And this is here the positive coating that I just referred to. So we've already talked about the order of electrophoretic migration. If you've got no charge, you don't move. The smaller you get with the same amount of charge, the larger your charge to size ratio, the faster you'll go. If we now add that up, we do that here. Yes, so the electrophoretic velocity, the speed, so the electrophoretic velocity here, the speed in electric field, is the mobility that we've seen in the plots, multiplied by the electric field strength. We can also predict the electrophoretic mobility based on the molecular properties of our ion, because it's the charge to size ratio, and the size is 6 pi times the radius, and it's the viscosity of the media, which typically is water, because most places will do aqueous separations. This all makes sense if we're talking about a single charge. Then our plot that we just showed makes sense. But life is more complex. We don't only have cations, we also have anions in the world. So we've got, this is the line that we've seen before, with little charge, slower than the smaller ones. We can mirror that for the anions. However, on this slide, I've put the zero charge, not actually at the intercept of the x and y axis. Any idea why I've done that? So if you are going out playing in a river that is flowing, and you've got a little inflatable boat, what happens if you don't pedal? So you're in a river, the river is slowly moving, you're in a boat, you're not putting any energy in, and you're not pedaling. What happens with your boat? Is your boat still, or is your boat moving? It's dragged by. These neutrals are being dragged by the electroosmotic flow. Be aware, if we've got a pump in our capillary, then not only are is driven by the velocity or by the electrophoretic mobility of the ion, the apparent mobility, the speed that we see, is the sum of the speed that's developed in the electric field plus the speed that the system, the water, the buffer, is being pumped through the capillary, because it's like a river. If you're in a lake, there's no movement, you're stagnant. If you're in a flowing system, so this point, this intercept, will therefore change with pH. Because if we're at low pH, we have low EOF, and therefore this will be at, the 0 point will be at 0. If we're at high pH, it will be sitting somewhere up there. So the electrophoretic mobility and the electroosmotic flow can be in the same direction, but it can also be in opposite direction. And that's why it's important to think of them as vectors. Because you may still be able, so if your electrophoretic mobility here is smaller than your electroosmotic mobility, then your apparent mobility, the rate that you move through the capillary, can actually still be positive. Because we've got less force going to the left than we have going to the right. So it is important to think about these mobilities as vectors and to add them up. Because we also can have beautiful situations for cations where the EOF and the electrophoretic mobility are in the same direction. So they go faster and faster because they're accelerated. It goes in the same direction. So it is important to know, if you're doing capillary electrophoresis, what's my electroosmotic flow doing, what is my analyte doing, and how do I get these to go in the direction I want them to go. Makes our separations faster and more efficient. So why don't we do everything at 120 kilovolts? We've got a thing that's called Joule heating. We pump a current through the capillary. A capillary is an electrical resistor. If our current becomes too high, we get a generation of heat. At around 100 degrees Celsius, our aqueous buffer starts boiling. That's not good for anyone. So we've got limitations. So if we look here at the same time scale, we can see that our peaks are a lot wider, taking a lot more time when we work at a low potential difference than at a higher one. So we go now into the point of our heat that is being generated during the separation. And our heat is a function of the current and the voltage we apply. So we've got the cathode and the anode again. We've got the electrolysis reactions taking place. And the heat that's being generated in this tube needs to be dissipated through the capillary surface. And that's why Jorgensen was so happy he thought about the use of narrow bore capillaries made of glass. Because glass is a very good thermal conductor, which means it's very good at dissipating the heat generated in the core to the outside. And typically a few silica capillary that is cooled by just blowing air over it, it can dissipate about 5 watts per meter. So how can we actually make an assessment on how good our separation is working? Are we having a problem with boiling? Because the fused silica capillary, it's brown, you can't look inside. I'd not recommend touching it because 20 kilovolts to your fingers, it tingles, it's really unpleasant. So how do you know if you've got actually a problem with heating in your capillary? And that is by plotting the potential that you apply versus the current, which is called an Ohm's plot. If life is good and beautiful, your Ohm's plot is linear. You increase your voltage, you increase your current. V equals I times R. Nothing is changing about your resistance, which means that you don't have a significant amount of heat being formed. What do you think happens with your resistance if it gets warmer? So your electrical resistance of an electrolyte, if your temperature increases from 20 to 50 degrees Celsius, does the resistance increase or decrease?
It's directly proportional.
Hmm?
It's proportional.
It's proportional, but does, so if you heat up a solution, do the ions move faster or slower?
Faster.
Faster. So your current gets higher, so your resistance comes lower. So if your temperature goes up, you get a higher current. And that's exactly what we see happening here. If we end up in the area where too much heat is being generated in our capillary, we increase our voltage, but we don't get a proportionate increase in our current. We get more increase in current than we expected based on our voltage increase. And that increasingly runs out of control up to the point that you get bubbles being formed. A bubble is an excellent insulator, which means as soon as you've got a bubble inside your capillary, your separation doesn't work anymore because you lose your electrical connectivity between your cathode and anode. So bubbles are kind of the end of your separation and you need to start again. So by plotting your voltage that you apply versus your current for the background electrolyte, for the buffer that you're working with, you can kind of say, well, this buffer, it's good to use to around 15 kilovolts. At 20 kilovolts, I get joule heating. I may be able to get away with a very short separation. But if I want to do long separations, it gets worse and worse because we get a buildup of heat because over time I generate more heat than I can dissipate and the temperature continues to increase. So with this background electrolyte, I wouldn't go much beyond 15 kilovolts to drive the separation because we end up deviating away from the ohmic behavior, and that means we'll end up in all kinds of problems, including changes of our electrophoretic mobility, because our electrophoretic mobility depends on viscosity. What happens with viscosity? Does that stay constant with an increase in temperature?
Decrease. It will decrease.
Yeah, which means that our analytes get faster, which means that we lose our ability to predict what's going on if we don't have the temperature under control anymore. So, play it safe, stay under the 15 kilovolts in this instance. So, as a chemist, we always like to separate more and better. What are the tools in the toolbox that we have to increase the efficiency of that separation? So we've got the apparent mobility is the sum of the electrophoretic mobility and the EOF. And we can control that with the properties of our analyte, which is our electrophoretic mobility, and our buffer, because the pH and the ionic strength of our buffer control the EOF. Diffusion constant, there's not that much we can do with it. Maybe play a little bit with the temperature. And then we've got the instrument-related components. We've got the potential that we apply and the length of the capillary that we cut. So they are the tools that we've got in the toolbox to manipulate our separation that we can play with in order to resolve ions that we want to detect. So with the ion, our ion has got a certain molecular weight and a structure that gives its geometry and therefore its hydrodynamic radius. Our analyte well may also have a pKa, which means that its size may be the same, but its effective charge may be dependent on the pH of the background electrolyte. And that's where developing CE separations becomes kind of a challenge, because you need to know a lot about what you're doing and everything is interconnected. So your electrophoretic mobility depends on the size and the charge, the effective charge, and it is therefore important to keep an eye on what the differences in pKa are between the analytes that you want to separate, because maybe you can tailor the pH of your separation to have one analyte deprotonated or more deprotonated than the other, and that pulls their mobility further apart. So it's a tool in order to realize that. So if the pH changes, most of you are chemists, so maybe this is not quite needed in here, but the mobility changes. So we've got the Henderson-Hasselbalch equation, where the pH is the pKa plus the log of the conjugate base over the weak acid, when we're talking about a weak acid. And that means here I made a plot of how the mobility changes for a couple of different ions. And of course we have our monodivalent ions. So here we've got monoprotic acid, took acetic acid here. And we can see that if we increase the pH, the mobility goes up. Ion increasingly gets deprotonated. pKa will be somewhere here, around 4.5, 5, that is correct for acetic acid. And then we're fully change anymore because we can't deprotonate the acetates even further. Adipic acid, which is a diprotic ion, we can see that we've got a little S-curve here. So we've got a first pKa sitting around 3. And then we can see, if we look at the curve, we've got another sigmoidal sitting here. So we've got a second pKa here around 4.5. Which means that we need to understand those two pKa's in order to manipulate the electrophoretic mobility. And we need to understand that there's areas where a very small change in pH can be a significant change in the mobility. But here at around pH 3.5 to 4, we actually kind of have a saddle, which means that our mobility is not going to be very sensitive on very small changes, and we may be able to have a very robust separation, even if our buffer that we've made up is not absolutely perfect. Then we've got the last example here is glutamine, which is a Zwitter ion. So we can see that at low pH, the basic groups are protonated. Then we end up at a pH range between 4 and 8 that were neutral. So electrophoretic mobility is 0. This is where we're deprotonated through anionic. And then we become cationic at pHs. That makes sense. So above pH 8, our nitrogen groups get protonated, which means we all of a sudden have a cation, which means that the direction of our migration changes. So it is important to understand. It also influences the viscosity. And it may help you modify the absorption to the wall or to a stationary phase. So selection of a buffer is very important in selecting the buffer, the electrophoretic conditions. And then we have our instrument conditions, which are the charge of our capillary wall. Native silica will be the negatively charged wall, but we can add permanent and dynamic coatings in order to change the charge at the wall. The length of the capillary and the voltage that we apply that combine into the electric field strength. So this graph is what you need to kind of in your head, or when I'm doing CE, it is stuck to my side of the instrument. Our CE separation can be influenced by our ion, which interacts with what we do in our buffer design, and our instrument properties. So if you know that you've got your ion and your buffer kind of right, you can optimize your instrument parameters to get the most favorable separation conditions. So when you're designing a separation, your electrolyte, it needs to have good buffering capacity. It needs to allow for enough heat dissipation, so you don't want it to be highly conducting. And you want to have not a lot of a new term that I'm introducing now, which is electromigrational dispersion, which is a funky name for calling peaks ugly peaks. The injection, I think, with the interest of time, let's go through quickly. So the injection can be done hydrodynamically, where you apply pressure to your sample vial and you get a little bit of sample injected. You can do it by making a height difference between your sample vial and your buffer, so you get siphoning of liquid from one to the other, or you can do it electrokinetic using a potential difference, which then allows you to inject using an electric field a small amount of sample into your capillary. It is important to realize that when you do electrophoresis, you've got an electrolytic cell, which means that we've got a generation of H+, NOH- at the anode and cathode respectively. The potential, and therefore we would like a small in our capillary, so we don't want to have a lower flow on the anodic side than on the cathode side, which means it is important that we've got a stable buffer. This is non-buffered, so this is a vial in a capillary electrophoresis instrument with pH indicator with the time in minutes, so 1, 2, 3, 4, 8, 16, and 16 on the buffered conditions minutes. And you see here the color of the pH indicator because of the protons being generated here. The pH changes, and you can see that this capillary will be increasingly taking in a background electrolyte of a different pH to what it originally started, unless we've got a buffered vial. And then we can see here that the tip of our capillary, you can just see it come through here, is in the same conditions during the whole run. So, as an electrophoregram, if we do our separation under buffered conditions, we get a nice and stable baseline and reasonably symmetric peaks. If we don't buffer, you can see that our baseline is getting all over the place and our peaks are a lot wider and it won't be as repeatable. So if we repeat this injection a couple of times in a row, it will always look slightly differently because the conditions in our capillary are not well controlled. So this demonstrates why it's very important in capillary electrophoresis to use buffers with a good buffer capacity. Then we come up with the electromigrational dispersion. And tomorrow with the simulations, it is Professor Subrit Bhagat will be getting continuing on this. It is important that our analytes have kind of the same speed as our co-ion, because when they're migrating through the capillary, we can't have two different ions at the same place in time. So our analyte ions are displacing the ion of the same charge in the background electrolyte. So if we've got an anionic analyte and the anion in our buffer, during our separation the analyte displaces the buffer. And it works the most elegantly if they have the same speed. So here we've got a separation in chromate, which is relatively fast ion in the buffer. And we can see that our fast ions here are really nice, beautiful, symmetrical peaks. But the slower analytes get, the more triangular, because our analytes are a lot slower and they need to try to displace that chromate, and they just can't because the chromate is too fast. At the same time, we've got here phthalate, which is a little bit slower. So we can see here that our analytes, our fast analytes, are actually too fast for good separation in phthalate because they're just too fast. Here we've got analytes with a similar mobility, particularly number 9 here, and we can see a nice symmetrical peak. And then we can see the same happening as we saw before in the chromate. Here we can see the peaks angled the other direction because our analytes are too slow for the phthalate. We can go to benzoate, which is even slower, and that means we get really, really nice peaks for our slow analytes, but really the slow ones, it becomes a little bit of a disaster and we can't even separate them anymore. Right. So if we've got a complex analyte set, it may actually not be sufficient to only have one co-ion in our buffer. In this instance, we've made a background electrolyte using chromate, phthalate, and benzoate all in the buffer. And you can see that allows us to have the whole analyte set really nicely separated in symmetrical peaks. So it is, if you want to minimize electromigrational dispersion, which is the tailing and the fronting of these peaks, if we've got a mismatch in mobility between our background co-ion and our analyte, we get ugly peaks. So if we've got an analyte with a very broad mobility distribution, we may want to have a combination of 2 or 3 different co-ions in there so that we allow for their displacement and in return are rewarded by getting nice symmetrical peaks and therefore separations with high plate numbers. So electromigrational dispersion is a fundamental phenomena. Match co-ion analyte, maximize the light concentration, provide too high current, and minimize the amount of analyte that's being injected. So small sample plugs make your peak look tidy as well. So if we want to choose our electrolyte, we want to control the pH, so we want to have a good buffer capacity. We want to minimize heat generation and maximize heat dissipation. So we want to, so our low conductivity biological buffers are typically preferred over our inorganic buffers because they quite typically have too high conductivity. And then we want to keep an eye on electromigration or dispersion by reducing the analyte concentration. So maybe you need to dilute your sample to increase the resolution, maximize the electrolyte concentration, keeping an eye on the fact that we want to minimize heat. So it's a compromise here. And we want to mobility match the background electrolyte co-ion. So in the optimization of a capillary electrophoresis method, we're kind of fighting and compromising in this triangle up to the point that we find an optimum. I think we're running close to an hour. So from an electropherogram, you can derive the parameters by having your migration times as well as the time of the EOF. We've got the equations here that I've already introduced before. You've got your electric field, that is your potential difference over your total length. So they are the instrument parameters that you set. Your apparent mobility is the length to the detector multiplied with the total length of your capillary divided by the voltage that you've applied and the migration time. And the migration time is the time that you're getting out here. If you take the times as they've come out here directly, then you've got your apparent mobility coming out. If you subtract your EOF from these times, so your EOF is at 9 minutes, your analytes are at 15 minutes. If you subtract that, then you get your effective mobility of your analyte corrected for the electroosmotic flow. And yeah, at home you can go through the calculations. I put them in merely so that you can see how you can get your figures of merit out of an electropherogram. So in summary, in capillary electrophoresis, analytes are separated due to the difference in electromigration velocity when an electric field is applied. So we need to have a potential difference applied across our system to get us to move. Like in HLE, you need to drive your separate. The apparent mobility is the analyte and the electroosmotic flow. Think about it as vectors. They can be in opposite directions. And whenever I'm working with a CE separation, I still draw my arrows upside down because sometimes it's just too many thinking steps and a couple of arrows make you realize what direction the world needs to go. So don't be afraid to just write things down. The background electrode and capillary dictate the separation mobility. The pH affects the charge and hence the mobility of your ion as well as that of the EOF. The separation efficiency is directly related to the applied field strength, but you need to take care to avoid Joule heating and to make sure that the pH is well controlled. So capillary electrophoresis, it is a bit of a balancing act. On the other hand, if you've got the balancing act well under control, I showed yesterday about the eco-detection system. We have electrophoretic separations that are running for months at a time without any human intervention and give us a whole suite of cations and anions when we swap the polarity. So capillary electrophoresis, it can be very stable, but you need to, if you're developing separations, you need to be very aware on how all the different elements are interlinked and make sure you select stable equilibria to make sure that your separations continue to be predictable. That was what I had to introduce you to capillary electrophoresis today before Professor Supreet Bhagat comes tomorrow, where you'll be working with some mobilities, doing some simulations yourself. If you've got any questions about CE, please feel free to ask me. I'm happy to answer. And if not, thank you for your attention. Very different to this morning.
We've covered all the basics.
Yeah, so it's not as common as HPLC, but